Imagine standing at the edge of the world's most inhospitable continent, where temperatures plunge to -89 degrees Celsius, and the sun vanishes for months at a time, expecting nothing more than the brutal physics of ice, wind, and isolation. Antarctica, a frozen expanse larger than Europe, has long been humanity's final frontier, a place where survival itself requires constant vigilance and where the harshness of the environment has been measured, documented, and understood through decades of scientific observation. Research stations dot the ice sheet, manned by geologists, physicists, climatologists, and engineers whose work relies on precision instruments, rigorous methodology, and the certainty that nature, however extreme, follows predictable rules. The continent's mysteries were thought to be geological, locked in ice cores and ancient rock formations, waiting to be decoded through patient analysis. Yet beneath the scientific certainty, beneath the carefully maintained research stations and the methodical collection of data, Antarctica harbours phenomena that resist explanation. These are not ancient legends passed down through oral tradition, not folklore embellished by generations of retelling, but documented incidents involving trained observers equipped with the tools of modern science. Time distortions recorded on multiple synchronized instruments, structures detected beneath the ice that defy geological models, acoustic patterns emerging from glaciers that suggest impossible complexity, and disappearances that leave behind evidence contradicting every rational explanation. In this investigation, we examine 25 mysteries from the frozen continent, each one challenging not just our understanding of Antarctica, but our certainty about the nature of reality itself. The thermometer read -89 degrees Celsius at Vostok Station on January 17, 1965, when Soviet meteorologist Dmitry Volkov noticed his wristwatch had stopped, though the wall clocks throughout the facility continued their steady progression. The research outpost, buried beneath the East Antarctic ice sheet at an elevation of 11,140 feet, was the most isolated human habitation on Earth, staffed by 12 scientists conducting atmospheric measurements and ice core analysis. Volkov had spent 3 months at the station, his body adapted to the thin air and crushing cold, his days structured by the routines that kept both equipment and men functional in conditions that tested the limits of human endurance. He tapped his watch, assuming the mechanism had frozen despite being rated for extreme temperatures, and returned his attention to the meteorological instruments arrayed before him. By mid-morning, 3 other researchers had mentioned similar problems with their personal timepieces, all of which had stopped within minutes of each other, despite being different makes and models. Chief Scientist Dr. Viktor Rusanov gathered the affected watches on the laboratory table, examining them under magnification while the facility's synchronized wall clocks continued ticking without interruption. The coincidence troubled him, though he suggested that perhaps the extreme cold had penetrated the research station more deeply than usual, affecting mechanisms that should have been protected. Volkov nodded, accepting the explanation, but felt a lingering unease that had nothing to do with temperature. The air inside the facility seemed thicker somehow, as though the atmosphere had gained weight, and his movements felt sluggish, requiring conscious effort to complete tasks that should have been automatic. Radio contact with Mirny Station, on the coast, scheduled for noon, revealed the first clear indication that something impossible was occurring. The communications officer at Mirny reported receiving Vostok's transmission at 11:47 a.m. by their chronometers, though Vostok's clocks showed 12:03 p.m. when the call connected. Rusanov insisted on verification, cross-referencing multiple time sources, but the discrepancy persisted. 13 minutes separated the 2 stations' perception of the present moment, with Vostok somehow existing slightly ahead of the outside world. The communications officer at Mirny suggested equipment malfunction, but Vostok's atomic clock calibrated before the winter isolation began, matched the facility's other timepieces exactly. Something had altered the flow of time within the research station, creating a temporal bubble whose boundaries remained invisible yet absolute. What disturbed the scientists more than the time discrepancy itself was the physical sensation accompanying it. Several researchers described feeling as though they were moving through water, their limbs responding with a delay that made precise work nearly impossible. Volkov attempted to pour tea and watched the liquid fall from the pot in what appeared to be slow motion, though his watch, now running again, suggested the action took the expected 2 seconds. Dr. Anatoly Kuznetsov, the station's physician, conducted reaction time tests and found that while the men's subjective experience suggested sluggishness, their actual response speeds remained normal by every measurable standard. The disconnect between perception and reality was so pronounced that 2 researchers reported nausea, their bodies struggling to reconcile what they felt with what instruments indicated. The phenomenon intensified throughout the afternoon as a faint mist began forming in the corridors, impossible at temperatures that should instantly freeze any moisture in the air. The vapour hung motionless, refusing to dissipate or settle, creating a haze that made the familiar passageways appear strange and distorted. Instruments measuring humidity showed readings near 0, yet the mist remained visible, tangible when researchers moved through it, leaving a cold dampness on exposed skin that evaporated within seconds. Rusanov photographed the phenomenon, the images later showing the mist as a faint shimmer rather than the substantial presence it appeared to be. One scientist claimed to see his breath condensing in the mist, despite the heated interior, while another reported hearing a low hum that seemed to emanate from the walls themselves, a vibration felt more than heard. By evening, Vostok Station was 27 minutes ahead of Mirny's timeline, according to radio synchronization checks, and the temporal drift showed no signs of stabilizing. The researchers gathered in the main laboratory, discussing whether to evacuate, despite the impossibility of transport in the depths of Antarctic winter. Rusanov recorded detailed observations in the station log, noting that while external conditions remained constant, wind speed steady at 15 km per hour, temperature holding at -89, something within or beneath the facility was warping the normal progression of time. The mist thickened as darkness fell, though no source could be identified, and the sensation of moving through resistant air became so pronounced that simple tasks required deliberate concentration. The distortion ended as abruptly as it had begun, the mist dissipating between 9:00 p.m. and 9:02 p.m. by Vostok's clocks, leaving the facility's air clear, and the oppressive thickness vanished. Radio contact confirmed that the station's timeline had synchronized with the outside world, the 27 lost minutes simply gone, absorbed back into whatever process had created the anomaly. The researchers' personal watches resumed normal function, and the physical sensations of sluggishness lifted completely, though several men reported persistent disorientation for days afterward, moments where time seemed to skip or stutter before settling back into familiar rhythms. Official Soviet scientific reports acknowledged equipment anomalies at Vostok on January 17, 1965, but provided no explanation for the temporal discrepancies or the physical symptoms experienced by the entire research team. Some dismissed the incident as a combination of isolation-induced stress and instrument malfunction, while others noted that 12 trained scientists with multiple synchronized timepieces and atomic clock verification created testimony difficult to discount entirely. The incident was classified under routine atmospheric research, the photographs of the impossible mist filed away, and the station's logs sanitized of the more disturbing details before being archived. Those who experienced the temporal distortion at Vostok carried memories of those hours that remained vivid decades later. Volkov, interviewed in 1991 after the Soviet Union's collapse, described the sensation of existing slightly outside normal time, watching events unfold at a pace that matched neither his perception nor his instruments. For the 12 men isolated at the bottom of the world, the distortion served as a reminder that Antarctica might harbour phenomena beyond the reach of standard physics, places where the rules governing time itself could bend without warning. To this day, researchers stationed at Vostok report occasional instrument anomalies, brief moments when clocks drift out of synchronization before correcting themselves, and the lingering sense that the ice beneath the station remembers what happened in those impossible hours. The crimson stain spreading across Taylor Glacier's face had been known since 1911, dismissed as iron oxidation by geologist Griffith Taylor and every researcher who examined it in the decades that followed. The Blood Falls, as the formation came to be called, appeared where subglacial meltwater emerged from beneath the ice, carrying dissolved iron that rusted upon contact with air and created the dramatic red cascade against white ice. It was geology, straightforward and unremarkable despite its visual impact, documented in scientific literature as an interesting example of iron-rich brine interacting with oxygen. Microbiologist Dr. Elena Cross approached the site on November 14, 2003, as part of a broader study of extremophile organisms in Antarctic environments, expecting to find hardy bacteria adapted to cold and darkness, nothing more. The samples she extracted from the outflow came from 3 meters beneath the glacier's surface, drawn through sterile drilling equipment designed to prevent contamination. Cross and her team transported the sealed containers to McMurdo Station's laboratory within hours, beginning analysis while the samples remained at sub-zero temperatures. Initial microscopy revealed bacterial presence, as anticipated, but the density surprised her. Where most Antarctic samples yielded sparse microbial populations, these showed concentrations similar to temperate ocean water, suggesting an ecosystem far more robust than the harsh conditions should support. The first cultures grew readily in the laboratory, multiplying at rates that contradicted the extreme cold and isolation from which they had been extracted. DNA sequencing began 2 weeks later, using equipment flown in specifically for the project, and the results appeared within days. Cross reviewed the genetic markers with growing confusion, cross-referencing the sequences against every database available to modern microbiology. The organisms contained DNA, carbon-based and structured along familiar double helix patterns, but significant portions of their genetic code matched no known classification. 17% of the sequenced material showed similarity to deep-sea bacteria found in hydrothermal vents thousands of miles north, organisms adapted to crushing pressure and superheated water. Another 12% resembled archaea from Antarctic dry valley soils, expected and unremarkable. The remaining sequences, comprising nearly 70% of the genome, aligned with nothing in any biological database. Cross conducted the sequencing 3 additional times, using fresh samples and different equipment to rule out contamination or procedural error. Each analysis produced identical results, the unknown genetic sequences repeating with perfect consistency. She expanded the testing to include metabolic analysis, discovering that the organisms processed sulfur compounds in ways that required biochemical pathways science had not documented. The bacteria appeared to function using mechanisms that should not work in their environment, extracting energy from chemical reactions that standard models suggested would be impossible at such low temperatures. Theoretical biochemists consulted on the findings could offer no framework for understanding how the metabolic processes operated. The discovery reached the broader scientific community through a cautiously worded paper published in March 2004, describing novel extremophile organisms with unclassified genetic material. Responses divided sharply along methodological lines. Some microbiologists argued that the unknown sequences represented ancient life forms, isolated beneath the glacier for millennia and evolving independently along pathways that diverged from all other terrestrial organisms. This theory positioned bloodfalls as a window into evolutionary possibilities that the rest of Earth's biosphere had never explored, a separate branch of life developing in complete darkness beneath Antarctic ice. Others proposed that contamination had occurred despite precautions, though they struggled to explain how human-introduced bacteria could match nothing in existing databases, or how contaminants would show such perfect genetic consistency across multiple samples. A smaller contingent of researchers suggested something more unsettling: the presence of deep-sea genetic markers in organisms extracted from beneath a glacier, combined with the unprecedented biochemical pathways, hinted at connections between Antarctic subglacial environments and ocean systems through mechanisms geology could not explain. No channels linked bloodfalls to the Southern Ocean, no underground rivers or aquifers that might transport organisms across such distances. The genetic similarities existed without any plausible transfer mechanism, as though the bacteria had somehow crossed impossible barriers or emerged from sources that remained hidden beneath the ice. Cross returned to bloodfalls in 2006, 2009, and 2012, each time extracting new samples and conducting increasingly sophisticated analyses. The organisms remained consistent across all collections, their unknown genetic sequences unchanged, their impossible metabolic processes continuing to defy explanation. Attempts to culture them in conditions mimicking their subglacial environment succeeded, but efforts to understand their evolutionary origin or classify them within established taxonomic frameworks failed. The bacteria simply existed, thriving in their dark world beneath the ice, carrying genetic instructions that connected them to nothing else science had documented. The outflow continues, iron-rich and crimson, staining Taylor Glacier as it has for uncounted centuries. Microbiologists who study the samples speak carefully about their findings, aware that claiming to have discovered life forms that defy classification carries implications for fields beyond microbiology. The organisms remain catalogued as extremophiles of unknown origin, their genetic mysteries preserved in frozen storage facilities, while researchers debate what their existence suggests about the nature of life itself and what else might lie hidden in Antarctica's lightless depths. The drill continued its rotation into the ancient ice on March 14, 1961, its motor humming steadily in the Antarctic silence, while the 6 scientists who had been operating it were nowhere to be found. A relief team from Vostok Station arrived at the remote drilling site 70 kilometers northwest of the main facility, expecting to rotate personnel and deliver supplies for another week of ice core extraction. Instead, they discovered a camp perfectly maintained, equipment functioning exactly as it should, and an absence so complete it seemed to press against the boundaries of the possible. The drill bit descended slowly through ice that had been compacted over millennia, its automated systems continuing the work that human hands had begun but would never finish. Senior researcher Dr. Pavel Grigorovich stepped from the transport vehicle into air that held the peculiar stillness unique to Antarctica's interior, where wind could vanish for hours and sound carried with unnatural clarity. The camp consisted of 3 insulated tents arranged in a triangle around the drilling apparatus, a generator providing steady power and supply crates stacked in precise rows that spoke to military discipline. Everything occupied its designated position, organized according to Soviet protocols that left no room for improvisation or disorder. Grigorovich called out, his voice echoing across the empty ice, and received only the mechanical response of the drill's motor in reply. Inside the main tent, he found a scene that would trouble him for the remainder of his career. 6 sleeping bags lay arranged along the tent's perimeter, personal items resting on makeshift shelves constructed from supply crates, photographs of families, books in various stages of being read with makeshift bookmarks indicating interrupted progress, and letters half written sat exactly where their owners had placed them. The small stove in the tent's centre held a pot containing frozen stew, the meal prepared but never consumed. Scientific instruments lined one wall, their readings current and accurate. Data logs filled with observations recorded in careful Cyrillic script up until the previous evening at 1947 hours. The other tents revealed similar scenes of interrupted daily life. Cold weather gear hung on designated hooks. Boots stood in neat pairs near the entrance flaps, and the emergency radio sat silent but functional, its last transmission logged as a routine status update, confirming normal operations and good weather. Grigorovich checked the transmission log twice, noting that the message had been sent at 20:15 hours on March 13th, less than 20 hours before the relief team's arrival. The 6 missing scientists had reported calm conditions, steady progress on the drilling operation, and no complications requiring attention. Nothing in their words suggested distress, confusion, or any awareness that within hours they would cease to exist in any location the search teams could find. What struck the search team as most troubling was the complete absence of footprints leading away from the camp despite fresh snow that had fallen during the night. The white surface surrounding the tents remained unmarked except for the tracks left by the relief team's own vehicles and boots. Antarctic snow preserved impressions with remarkable fidelity, capable of holding the details of boot treads for weeks when conditions remained stable. 6 people could not have departed the camp without leaving evidence of their passage. Yet the ice showed no signs of human movement beyond the established paths between tents and the drilling equipment. It was as though the researchers had simply dematerialized, their physical presence erased without disturbing a single snowflake. Grigorovich organized a systematic search pattern, radioing Vostok for additional personnel and equipment, while his team examined every meter of ice within a kilometer radius of the camp. Aircraft arrived the following day, flying low over the surrounding terrain, while observers scanned for any indication of the missing scientists. Ground teams worked in expanding circles, probing crevasses and checking for signs of ice collapse that might have swallowed the researchers, but the bedrock beneath this region of Antarctica lay at a depth of more than 2,000 meters, covered by ice so stable it had not shifted measurably in decades. Geological surveys confirmed no recent seismic activity, no sudden formation of crevasses, no environmental change that could account for the disappearance. The search continued for 3 weeks, eventually involving more than 40 personnel and covering an area of 500 square kilometers. Every piece of safety equipment remained at the camp, including the emergency locator beacons each researcher wore attached to their cold weather gear. The beacons, designed to activate automatically in cases of distress or separation from the main camp, transmitted nothing. Radio monitoring detected no signals, no brief bursts of communication that might indicate to survivors attempting contact. The vast white emptiness offered no clues, no bodies, no scattered equipment, no trace that 6 trained scientists had existed anywhere beyond the confines of the camp they had abandoned. Soviet authorities classified the incident as a tragic accident, though the official reports provided no specific explanation for what had occurred. Internal documents, released decades later, revealed that investigators had considered multiple scenarios, including navigation error leading the team into a whiteout, sudden illness, or contamination requiring evacuation, and even the possibility of defection. Though none of these theories aligned with the physical evidence, the abandoned cold weather gear alone contradicted any voluntary departure, as no one familiar with Antarctic conditions would venture into the environment without proper protection. The drilling equipment sat silent now, its motor finally shut down by the relief team after running continuously for more than 30 hours. Ice cores extracted before the disappearance were transported back to Vostok, analysed and filed away, their data contributing to climatological records without acknowledgement of the circumstances under which they had been obtained. The camp itself was dismantled, its components distributed to other research stations, though some personnel reported an unwillingness to use equipment from the site, citing superstition that scientists claimed to dismiss but could not entirely shake. Families of the missing researchers received notice that their loved ones had perished in an unspecified accident, their bodies lost to Antarctic conditions. No memorial could mark the location where 6 people had vanished, as the ice sheet's slow movement would carry any monument away from its original position within years. The drilling site exists now only in archived coordinates, a point on maps that marks where reality proved more fragile than the scientists who encountered its breach could have anticipated. When satellite technician Marcus Whitmore reviewed the ground-penetrating radar images of the Ellsworth Mountains in December 2016, the perfectly symmetrical angles appearing beneath 2 miles of ice made him call his supervisor immediately. Whitmore had spent 3 years analysing Antarctic geological data for the British Antarctic Survey, examining radar returns that mapped bedrock topography hidden under the ice sheet, and he understood the difference between natural rock formations and geometric precision. The images on his screen showed structures with angles measuring exactly 90 degrees at multiple points, edges that ran in parallel lines for more than a kilometre, and a symmetry that should not exist in geological formations shaped by tectonic forces and erosion. He saved the data, cross-referenced the coordinates, and confirmed that the anomaly was real before making the call that would ignite a controversy spanning disciplines. The initial findings came from synthetic aperture radar mounted on satellites orbiting Earth, technology designed to penetrate ice and map the continent's hidden landscape. The Ellsworth Mountains, a range extending for more than 300 kilometres across West Antarctica, had been surveyed multiple times, but improvements in radar resolution during the 2010s revealed details that earlier scans had missed. The structures appeared at coordinates deep within the range, buried under ice estimated at 3,000 metres thick. Ground-penetrating radar from aircraft flying at lower altitudes confirmed the satellite observations, showing not 1, but 3 distinct formations arranged in a triangular pattern, each separated from its neighbours by approximately 12 kilometres. Dr. Catherine Henley led the analysis team tasked with determining whether the structures were natural or required alternative explanations. A geomorphologist with 2 decades of experience studying mountain formation processes, Henley approached the data with skepticism born from years of seeing patterns in nature that the human mind wanted to interpret as artificial. Mountains formed through uplift, folding, and volcanic activity rarely produced clean angles or parallel lines, yet the radar returns showed precisely those characteristics. She measured the structure's dimensions carefully, finding that the largest reached a base width of 1,200 metres and a height of approximately 400 metres from the surrounding bedrock, proportions similar to the Great Pyramid of Giza, scaled up by a factor of 3. The symmetry proved most difficult to explain through conventional geology. All 3 structures showed the same basic shape, variations so minor they fell within the margin of measurement error. Their faces aligned to cardinal directions with less than 2 degrees of deviation, an orientation that plate tectonics and erosion should randomize over geological time. Ice core samples taken from sites near the structures dated the covering ice sheet to more than 34 million years, suggesting that whatever lay beneath had been entombed since the Eocene epoch when Antarctica's climate shifted from temperate to frozen. If natural, the formations had somehow maintained their geometric precision through tens of millions of years of ice loading and glacial movement, processes that typically fractured and reshaped bedrock over far shorter periods. Competing theories emerged quickly from the geological community. Some researchers argued that the structures represented nunataks, mountain peaks composed of unusually resistant rock that had been eroded into pyramid-like shapes before being buried by the expanding ice sheet. This explanation required specific rock types and erosion patterns working in concert to produce identical results at 3 separate locations, a coincidence that strained probability but remained theoretically possible. Others proposed that volcanic activity had created the formations, magma forcing its way through existing rock and cooling into geometric patterns. Volcanic plugs could produce angular structures, though typically at much smaller scales and without the precise orientations observed in the radar data. A smaller contingent suggested that these structures might be artificial, constructed before the ice sheet's formation by a civilization that geological history had no record of. This theory faced immediate criticism from multiple disciplines. Archaeological evidence placed modern human evolution well after Antarctica's glaciation, and no known hominid species possessed the technological capability to construct monuments on such a scale. The hypothesis required either revising the timeline of human development or proposing a separate, unrelated civilization that had somehow left no other trace of its existence. Most researchers dismissed this possibility as incompatible with established science, though they acknowledged that the structure's characteristics made conventional explanations problematic. Ground expeditions to the site proved impractical, given the ice depth and the structure's location in one of Antarctica's most inaccessible regions. Drilling through 3,000 meters of ice would require resources exceeding what any single research program could provide, and even if the structures could be reached, removing enough ice to expose them for direct examination would take years of continuous work. The formations remained visible only through radar imaging, their nature interpretable only through indirect measurement and computer modeling. Henley's team created 3-dimensional reconstructions based on the data, generating detailed models that could be examined from any angle. Yet the models could only reflect what the radar had detected, and radar could not determine whether the smooth faces it mapped were naturally weathered rock or artificially shaped surfaces. The scientific community remained divided. Papers published in geological journals arguing for natural formation, while others highlighted the statistical improbability of the observed characteristics occurring without design. Conference presentations generated heated discussions between researchers who found the geometric precision troubling and those who insisted that nature produced apparent patterns through processes that appeared random but followed underlying physical laws. The debate continued without resolution, hampered by the impossibility of obtaining definitive evidence buried under miles of ice. The structures remain entombed beneath the Ellsworth Mountains, their true nature locked away, where neither drilling equipment nor human observation can reach them. Satellite surveys continue to refine the measurements, each new data set confirming the original findings without bringing clarity to their interpretation. For geologists who study the images, the formations represent either an extraordinary coincidence of natural processes or evidence that Antarctica's geological history contains chapters that current science has not yet read. The hydrophone array registered the sound at 2:17 a.m. on June 3, 2012, a deep, resonant pulse that marine biologist Sarah Chen initially assumed was whale song, until the pattern repeated with mathematical precision every 73 seconds for the next 6 hours. The underwater monitoring station in McMurdo Sound had been operational for 8 months. Its sensitive microphones designed to track the movements and vocalizations of Weddell seals and Antarctic minke whales in the waters beneath the Ross Ice Shelf. Chen had analysed thousands of hours of recordings, learning to distinguish between the click trains of foraging seals, the low-frequency moans of distant whales, and the crack and groan of shifting ice. This sound matched none of them. She isolated the frequency range, finding that the pulse is centered around 52 Hz, with harmonic overtones extending up to 180 Hz, a profile that fell within biological possibility for large marine mammals. The duration of each pulse measured 2.3 seconds, followed by silence of exactly 70.7 seconds before the next pulse began, a consistency that natural biological processes rarely maintained. Whale songs varied in timing, seals adjusted their vocalizations based on environmental feedback, and ice produced random acoustic events as stress accumulated and released. Chen ran the recording through pattern recognition software designed to identify artificial signals, and the program flagged the sounds as potentially non-natural, though it could not provide a classification. By dawn, the phenomenon had persisted for 6 hours and 12 minutes, during which the timing never deviated by more than 0.3 seconds from the established pattern. Chen contacted Dr. Michael Torres, the station's acoustic specialist, who arrived at the monitoring room to review the data with the skepticism of someone who had investigated dozens of anomalous sounds that eventually resolved into mundane explanations. He listened to the recording, watched the spectrograph display the frequency patterns, and examined the timing data before admitting that he could offer no immediate identification. The sound's characteristics fell into an uncomfortable middle ground between biological and mechanical, exhibiting regularity that suggested purpose without matching any known source. Attempts to triangulate the origin using the array's multiple hydrophones produced confusing results. The sound appeared to emanate from directly beneath the monitoring station, at a depth the instruments could not precisely determine, somewhere between 400 and 800 meters below the ice. That depth range placed the source well below the ice shelf's underside, but above the seafloor, suggesting a source suspended in the water column or moving at a depth that varied slightly over time. Torres deployed additional hydrophones on longer cables, lowering them to 600 meters in an attempt to narrow the source location, but the new instruments detected nothing. The sound reached only the original array, as though its propagation followed selective paths through the water. Analysis of the acoustic properties revealed additional strangeness. Sound travels through water at approximately 1,500 meters per second, varying with temperature and salinity, and this consistency allows researchers to calculate distance from time delays between sensors. The pulses detected by Chen's array showed time delays inconsistent with point source propagation, arriving at different hydrophones in sequences that suggested the sound was either being reflected in impossible ways or originating from multiple locations simultaneously. Computer models attempting to reconstruct the source position produced error messages, their algorithms unable to reconcile the contradictory data. The phenomenon ceased at 8:29 am as abruptly as it had begun, the final pulse fading into the ambient noise of the sound, without any change in pattern or intensity to suggest gradual shutdown. Chen and Torres continued monitoring for the remainder of the day, hoping for recurrence that might provide additional data, but the hydrophones detected only normal Antarctic marine sounds. They filed a report with the National Science Foundation detailing the event, including spectrograms, timing analysis, and their failed attempts at source identification. The report joined similar documents from other Antarctic research stations, incidents where instruments had detected sounds that defied classification before disappearing without explanation. 3 months later, on September 18th, the pattern returned, this time lasting only 40 minutes and repeating every 91 seconds instead of 73. The frequency profile matched the earlier recording, but the timing had changed, suggesting either different conditions affecting transmission or intentional variation in the source. Chen captured the entire event, comparing it in real time with the June recording and noting that while individual pulses were nearly identical in acoustic structure, their temporal organization followed a different sequence. Over the following 2 years, the sounds appeared 7 more times, each occurrence differing in duration and repetition rate while maintaining the same basic acoustic signature. Researchers examining the accumulated data noted that the timing patterns, when converted to numerical sequences, showed relationships that appeared non-random. The intervals between pulses, measured in seconds and converted to integers, sometimes formed prime number sequences or mathematical progressions that probability analysis suggested were unlikely to occur naturally. This observation deepened rather than resolved the mystery, as it raised questions about whether the sounds carried information encoded in their timing, or whether pattern-seeking human minds were imposing structure onto randomness. The hydrophones in McMurdo Sound continue their patient listening, recording the acoustic landscape of Antarctic waters, while operators monitor for the return of the structured pulses. Each new detection is analysed, archived, and added to a growing database of sounds that resist explanation, their origins remaining as hidden as the dark water from which they emerge. Geologist Robert Marsh stopped mid-stride in the Wright Valley on December 8, 1993, staring at the mummified seal corpse lying in the gravel 45 miles from the nearest ocean, its preservation so perfect he could still see individual whiskers. The dry valleys of Antarctica, a region of exposed rock and soil where annual precipitation measured less than 10 centimeters and humidity remained near zero, created natural mummification conditions unmatched anywhere on Earth. Organic material placed in this environment would desiccate within weeks, tissues preserved indefinitely by the combination of extreme cold, arid air, and the absence of decomposing bacteria. Marsh understood these processes, had studied the valley's unique conditions for 2 field seasons, but the seal's presence made no sense regardless of preservation quality. The animal lay approximately 3,000 feet above sea level, positioned on ground that showed no evidence of recent water flow or flooding. Seals required ocean access for feeding and could not survive extended periods away from water, making their presence this far inland a biological impossibility under current conditions. Marsh examined the surrounding terrain carefully, searching for dried stream beds, ancient shorelines, or any geological feature that might explain how a marine mammal had reached this location. The valley's topography showed the characteristic U-shape of glacial carving, but the glaciers that had formed it had retreated millions of years ago, and no waterway connected this site to McMurdo Sound or any other body of water. Carbon dating of tissue samples, conducted at the Crary Science and Engineering Centre, placed the seal's death at approximately 1,200 years ago, well within the period when Antarctica's climate matched current conditions. The animal had not died during some ancient epoch, when the continent might have been warmer or ice sheets positioned differently. It had perished during the medieval warm period, when human civilizations flourished in the northern hemisphere, and Antarctica remained as frozen and isolated as it stood today. The dating results eliminated theories about dramatically different past environments and focused attention on the mechanism of transport. Additional seal carcasses discovered over the following decade deepened the mystery rather than resolving it. By 2005, researchers had documented 47 individual seals scattered across the dry valleys, ranging in elevation from 2,800 to 4,100 feet above sea level, and located as far as 62 miles from open water. Carbon dating revealed ages spanning from approximately 500 years to more than 3,000 years before present, indicating that whatever process deposited the seals had occurred repeatedly across millennia rather than representing a single catastrophic event. The carcasses showed no signs of predation or scavenging, and their position suggested they had simply stopped moving and died where they lay, rather than being carried to these locations after death. Theories attempting to explain the phenomenon encountered immediate difficulties with physical constraints. The most obvious explanation that Storms or unusual high water events had transported the seals inland, required waves or flooding reaching thousands of feet above sea level, across terrain, with no channels or depressions to guide water flow. No Antarctic storm in recorded history had produced flooding on such a scale, and geological evidence showed no indication of massive water movements through the dry valleys during the time periods when the seals died. The hypothesis required environmental conditions so extreme they fell outside the bounds of known Antarctic climate patterns. Others proposed that the seals had travelled inland voluntarily, perhaps disoriented by illness or magnetic anomalies that disrupted their navigation. Southern elephant seals occasionally ventured short distances onto shore, but even these largest of Antarctic seals, weighing up to 4 tons, could not cross 45 miles of rough terrain while climbing 3,000 vertical feet. The energy expenditure would kill them long before they reached the locations where the carcasses were found, and none of the mummified seals showed evidence of the severe emaciation that such a journey would produce. Their body condition suggested they had been healthy at the time of death, further contradicting the theory of voluntary migration. A third explanation involved changes in ice sheet configuration, proposing that during certain periods the Ross ice shelf had extended further inland, bringing ocean water closer to the dry valleys and allowing seals to reach higher elevations before ice retreat stranded them. This theory aligned better with the physical evidence but faced significant chronological problems. Ice core data and glacial modelling indicated that ice sheet extent during the past several thousand years had remained relatively stable, showing fluctuations measured in kilometres rather than the tens of kilometres required to explain seal presence at documented locations. The ice would have needed to advance and retreat multiple times across vast distances, leaving geological traces that researchers could not find. The mummified seals rest in the positions where death claimed them, their bodies transformed into desiccated monuments to an impossible journey. Researchers who examine them catalogue the growing number of discoveries, noting patterns in distribution and age that hint at underlying causes without revealing what those causes might be. Each new carcass adds data to a mystery that refuses to yield to conventional explanations, suggesting that Antarctic environments contain transport mechanisms or historical conditions that current science has not yet identified. The valleys hold their silence, and the seals, frozen in time by the preserving air, offer no testimony beyond the impossible fact of their presence. When the underwater camera footage from the USNS Eltanin was developed on August 29, 1964, showing a perfectly symmetrical, antenna-like structure rising from the Antarctic ocean floor at a depth of 13,500 feet, marine biologists could not identify what they were seeing. The research vessel had been conducting a bathymetric survey along the route from Cape Horn to McMurdo Sound, part of a broader program mapping the Southern Ocean's seafloor topography and documenting deep-sea biological communities. The camera, lowered on a cable and triggered at regular intervals as it descended, captured images of sediment, occasional starfish, and the expected barren landscape of the abyssal plain. Then at coordinates 60 degrees south and 90 degrees west, it photographed something that should not exist at that depth. The structure measured approximately 2 feet in height, according to scale references in the frame, rising from the seafloor in a central shaft with multiple symmetrical nodes extending outward at regular intervals. Its appearance suggested manufactured precision, with branches or protrusions arranged in a pattern that resembled a radio antenna or perhaps an elaborate candelabra. The object appeared rigid, maintaining its upright position despite the strong bottom currents known to sweep across that region of the seafloor. Sediment accumulation at its base indicated it had occupied that position for considerable time, though the structure itself showed no signs of the biological fouling that typically covered any solid surface exposed to deep ocean conditions for extended periods. Marine biologist Dr. Thomas Hopkins examined the photographs upon the Eltanin's return to port, distributing copies to colleagues specializing in deep-sea organisms and geological formations. The initial consensus held that the structure must be biological, perhaps a sponge or some unknown species of Cnidarian that had developed an unusually regular growth pattern. Deep-sea sponges occasionally exhibited geometric arrangements, their silica spicules organizing into frameworks that could appear artificial to untrained observers. Hopkins requested analysis from experts in porifera taxonomy, providing them with enlarged images that showed the structure's details as clearly as the camera's resolution allowed. The sponge hypothesis encountered difficulties as specialists examined the photographs more closely. Deep-sea sponges, regardless of species, showed variations in their structural elements that reflected individual growth patterns and environmental influences. The Eltanin structure displayed uniformity inconsistent with biological development, its nodes positioned at intervals that varied by less than the camera's ability to measure. The branches maintained consistent diameter along their length, rather than tapering as organic structures typically did, and the central shaft rose at an angle perpendicular to the seafloor with a straightness that biological tissue under pressure rarely achieved. Sponge experts could not identify any known species matching the photographed characteristics, but they also acknowledged that deep-sea taxonomy remained incomplete, with new species discovered regularly in abyssal environments. Alternative biological explanations proved equally problematic. Sea pens, colonial organisms that could form upright structures on the seafloor required depth shallower than 3,000 feet, where phytoplankton provided adequate nutrition. At 13,500 feet, the pressure exceeded 6,000 pounds per square inch, and no light penetrated from the surface, eliminating photosynthetic organisms from the food chain. Any life at that depth survived on organic material drifting down from shallower waters or through chemosynthesis near hydrothermal vents. The Eltanin structure showed no characteristics consistent with vent-adapted organisms, and its location placed it far from any known geothermal activity. Geological explanations faced similar constraints. Manganese nodules could form on abyssal plains, their growth driven by mineral precipitation from seawater, but these structures developed as rounded masses rather than vertical projections with regular branching. Volcanic formations occasionally produced columnar structures through basalt cooling, yet these formed in massive hexagonal columns at scales of meters to tens of meters, not the delicate branching visible in the photographs. No known geological process could account for the observed symmetry at the documented scale. The artifact hypothesis, suggesting human construction or deployment, required explaining how an object reached a depth that only specialized equipment could access in 1964, and why anyone would place such a structure in one of Earth's most remote and inaccessible locations. Deep submersibles capable of reaching 13,500 feet existed but remained rare and expensive, their deployment documented and publicized. No records indicated any deep-sea operations in that region before the Eltanin survey, and the sediment accumulation suggested the structure had been in place for years rather than months. Subsequent expeditions attempted to relocate the structure using the original coordinates, but the search efforts failed to find it. The Antarctic seafloor's vastness, combined with the imprecision of 1964 navigation systems, meant that even a few hundred meters of position error would place searchers beyond visual range of a 2-foot object. Bottom currents could have toppled the structure in the intervening years, or sediment could have buried it beyond detection. Some researchers suggested that the photographs documented something temporary, perhaps biological after all, that had simply died and disintegrated in the decades since the original images were captured. The Eltanin antenna, as the structure came to be called in publications discussing unusual Deep-sea findings occupies an uncertain position in marine biology. The photographs exist, archived in research databases, and reproduced in papers examining unexplained oceanic phenomena. Their clarity sufficient to show that something unusual appeared before the camera, but insufficient to permit definitive identification. Whether the structure represented an unknown organism adapted to conditions science has not fully characterized, a geological formation produced by processes not yet understood, or something else entirely, it served notice that the deep ocean surrounding Antarctica contained mysteries that single photographs could reveal but not resolve. Norwegian glaciologist Henrik Andersen stepped into the complete whiteout enveloping the Amundsen Scott South Pole Station on November 12, 2007, for what he believed was a 10-minute walk to the equipment shed, only to return and discover that 3 minutes had passed according to every clock in the facility. The phenomenon known as whiteout occurred when overcast skies, blowing snow, and the uniformly white landscape combined to eliminate all visual reference points, creating conditions where horizon, ground, and sky merged into featureless brightness. Experienced polar workers understood the disorientation whiteouts produced, the way the brain struggled to maintain balance without visual cues, but Andersen's experience suggested something beyond perceptual confusion. He had traversed the route between the main station and the equipment shed hundreds of times during his 6-month deployment, knew the distance measured exactly 180 meters, and could walk it blindfolded if necessary. The whiteout had descended suddenly during his afternoon equipment check, visibility dropping from several hundred meters to less than 3 in a matter of minutes. Andersen had tied a safety line to the station's exterior anchor point before venturing out, standard procedure that allowed personnel to find their way back by following the rope even when they could see nothing. He remembered walking the full distance to the shed, entering through the insulated door, conducting his inspection of the seismic monitoring equipment, and returning along the safety line to the station entrance. Inside, he checked his watch against the wall clock, expecting to see that 12 to 15 minutes had elapsed. Instead, both timepieces showed that he'd been gone for 3 minutes and 40 seconds, insufficient time to have walked even one direction, let alone completed the round trip and his inspection tasks. Andersen questioned the station manager, Dr. Claire Yoshida, who confirmed that she had watched him leave, monitored the time, and noted his quick return, with some surprise. The safety line showed no signs of having been pulled taut or walked along twice, and the seismic equipment logs indicated that Andersen had indeed powered up the monitoring interface, a task requiring at least 2 minutes of sequential operations. Over the following months, similar incidents accumulated in reports from multiple Antarctic stations. A British researcher at Halley Station described spending what felt like an hour repairing a weather instrument during a whiteout, only to learn that colleagues had timed his absence at 11 minutes. An American technician at McMurdo walked to a storage facility during whiteout conditions, experienced what she estimated as a 20-minute search through supply containers, and returned to find that 90 seconds had passed. A Japanese scientist at Siowa Station reported the opposite effect, a brief walk to check an antenna array that felt like 5 minutes, but consumed 40 minutes, according to station chronometers and the worried colleagues who had been about to initiate a search. The discrepancies consistently appeared during whiteout conditions, never during clear weather or normal reduced visibility. Researchers who experienced the temporal distortions described physical sensations accompanying the time loss, a heaviness in the limbs similar to moving through water, occasional dizziness that had no clear medical cause, and in several cases, profound exhaustion disproportionate to the physical effort expended. Medical examinations revealed elevated cortisol levels and patterns of muscle fatigue consistent with exertion lasting far longer than the objective time periods involved. Blood oxygen saturation remained normal, ruling out hypoxia, and neurological assessments found no evidence of seizures or other conditions that might produce memory gaps. Attempts to document the phenomenon scientifically faced immediate difficulties. Installing monitoring equipment to track researchers during whiteouts proved impractical, given the unpredictability of when conditions would occur and which personnel would be affected. GPS tracking showed normal movement patterns and speeds, with subjects traversing the expected distances at walking pace without unexplained delays or acceleration. Heart rate monitors revealed elevated pulse rates, consistent with physical activity, but provided no insight into why subjective time perception diverged so dramatically from objective measurements. Video cameras mounted on equipment sheds recorded subjects arriving and departing at intervals matching the shorter objective timelines, not the longer periods the subjects remembered experiencing. Psychological explanations suggested that the sensory deprivation produced by whiteouts might alter time perception, causing minutes to feel like hours or compressing extended periods into brief moments. Human time estimation relied heavily on environmental cues, changes in light, sounds, visual stimuli, and the absence of these cues could distort internal clocks. Studies of sensory deprivation had documented time perception anomalies, though typically with subjects estimating durations too short rather than too long, and never with the physical fatigue that Antarctic personnel all reported. The consistency of the accounts across different stations, different individuals, and different circumstances suggested something more systematic than individual perceptual errors. Others proposed that extreme cold combined with the unique atmospheric conditions above Antarctica might affect brain function in ways that disrupted short-term memory formation, creating gaps that consciousness filled with false memories of extended activity. This hypothesis required neural effects that no medical research had documented and failed to explain the physical evidence of tasks completed, equipment operated, and distances travelled during periods that clocks insisted were impossibly brief. The safety lines showed appropriate wear patterns for the distances subjects claimed to have walked, and equipment logs confirmed operations that required sequential steps and specific time durations. The phenomenon persists without resolution, documented in station logs and incident reports that accumulate each Antarctic season. Personnel briefings now include warnings about time perception distortions during whiteouts, advising researchers to rely on instruments rather than subjective experience when estimating durations. Some stations have implemented buddy systems for whiteout travel, pairs of researchers who can compare experiences and potentially identify when temporal anomalies occur. The data continues to accumulate, dozens of incidents spanning 2 decades, each one adding detail to a mystery that offers no clear answers about why whiteout conditions seem to alter not just perception, but the relationship between experienced time and measured time in ways that leave physical traces contradicting the objective record. The sonar pulse sent into Lake Vostok on February 5, 2001, should have returned a clear echo from the lake bottom at the expected depth of 1,000 meters, but instead, geophysicist Anton Petrov watched the equipment register something impossible, a void beginning at 1,200 meters and extending downward into nothing. Lake Vostok, discovered beneath the East Antarctic ice sheet in the 1970s through ice-penetrating radar, represented one of Earth's largest subglacial lakes, sealed beneath more than 2 miles of ice for an estimated 15 million years. The lake's existence had been confirmed through multiple surveys, its dimensions mapped with increasing precision as technology improved, and by 2001, researchers understood its basic characteristics. It measured roughly 250 kilometers long and 50 kilometers wide, contained liquid water maintained above freezing by geothermal heat and the insulating pressure of overlying ice, and rested in a depression carved into ancient bedrock. Petrov's survey used seismic reflection techniques, generating sound waves that traveled through the ice, passed through the water column, and bounced back from the lake floor, allowing precise depth calculation based on the time delay between transmission and wire reception. The method had mapped thousands of subglacial features across Antarctica with reliable accuracy. Equipment calibration showed normal function, and multiple test pulses confirmed that the sonar operated within specifications. The first anomalous reading appeared while mapping the lake's deepest section, a region where previous surveys had indicated stable bedrock at approximately 1,000 meters below the ice-water interface. The returning echo showed the expected reflection at that depth, but additional signals suggested something below it, a space where sound waves penetrated further before either being absorbed or reflecting from a boundary the equipment could not clearly resolve. Additional sonar sweeps over the following days confirmed the anomaly's presence across a roughly circular area measuring 30 kilometers in diameter. Within this region, acoustic returns became confused, showing layered echoes that suggested alternating zones of different density or composition. The void, if it could be called that, began at depths between 1,250 and 1,250 meters, depending on the specific location surveyed, and extended downward for at least 400 additional meters before signals became too weak or distorted to interpret. The acoustic properties matched neither water, which should produce clear transmission and distant bottom echoes, nor rock, which should return strong reflections from the first solid surface encountered. The return suggested empty space or material so acoustically transparent that sound passed through it without significant reflection. Gravitometric surveys conducted from ice surface stations detected density variations consistent with a large void or low-density material beneath the lake. The gravity field in the anomalous region measured slightly lower than surrounding areas by approximately 2.3 milligauss, a difference small but significant when integrated across the affected area. Calculations based on the gravity deficit suggested a volume of reduced mass, equivalent to a cavern, more than 1 cubic kilometre in extent, though the shape and precise dimensions remained uncertain. No geological process known to operate in this environment could create such a void, and the stable nature of the surrounding rock argued against recent tectonic activity that might have fractured bedrock and created empty spaces. Theories attempting to explain the void encountered immediate problems with basic physics and geology. If the space contained water at lower temperature or different salinity than the main lake, it should still produce acoustic returns that sonar could interpret. Yet the signals suggested minimal reflection. If the void represented a gas-filled cavity, the pressure at 1,200 meters depth, roughly 120 atmospheres, should compress any gas to densities approaching liquid, eliminating the acoustic void effect. If the space contains sediment or porous rock, the acoustic properties should differ from what instruments detected, showing gradual signal attenuation rather than the sharp boundary observed. Some researchers proposed that the void might be an artifact of complex acoustic paths, sound waves refracting through water layers of varying temperature or salinity and creating false echoes that instruments misinterpreted as deep structures. This explanation required temperature or salinity gradients steep enough to bend sound significantly, conditions that thermal modelling of the lake suggested should not exist given the uniform geothermal heating and the millions of years available for mixing. Subsequent surveys using different frequencies and angles of incidence produced similar results, arguing against simple acoustic mirages. The Russian drilling project approaching Lake Vostok from above proceeded with extraordinary caution, aware that penetrating the ice-water boundary risked contaminating a pristine environment that might harbour unique microbial life. The presence of the anomalous void added another concern. If the drill reached the lake and instruments lowered into the water detected something unexpected at depth, the expedition's mandate to avoid contamination might prevent investigation. Plans called for sampling only the uppermost water layers, leaving the deep lake undisturbed, which meant the void would remain beyond direct observation, regardless of drilling success. International protocols eventually required that the borehole be sealed before reaching the lake proper, preventing any direct contact that might introduce surface contamination. The decision left Lake Vostok largely unexplored, its waters dark and sealed, the void beneath its deepest point remaining inaccessible to human investigation. Seismic and gravity surveys continue when research budgets allow, refining the anomaly's boundaries and characteristics without bringing clarity to its nature. The void persists in datasets and scientific publications, a region of Lake Vostok where instruments detect something that should not exist beneath a lake that should not contain empty spaces at those depths. Helicopter pilot James Rutherford watched his compass needle spin in complete circles as he approached the Fosdick Mountains on January 22, 2005, while his GPS unit flickered between coordinates separated by hundreds of miles, forcing him to navigate by visual landmarks alone. Rutherford had logged more than 800 flight hours over Antarctic terrain, ferrying scientists and supplies between research stations and field camps, his experience teaching him to expect equipment anomalies in the extreme environment. Compasses could show temporary deflections near certain rock formations. GPS signals occasionally weakened when satellites dropped below the horizon, and electronic systems sometimes malfunctioned in the severe cold. The behaviour his instruments displayed during the Fosdick Mountains approach exceeded anything in his operational experience. The compass had begun its rotation approximately 40 kilometres from the mountains, starting with minor oscillations that Rutherford initially attributed to local magnetic variations common in volcanic regions. As the helicopter continued its approach, the oscillations increased in amplitude until the needle moved in steady clockwise circles, completing one full rotation every 3 seconds. Simultaneously, the GPS display began showing position fixes that jumped erratically, placing the aircraft alternately near the intended coordinates, 200 kilometers to the east, and at one point briefly indicating a location in the Southern Ocean. The backup GPS unit, operating independently on a separate power system, exhibited identical behavior, ruling out single system failure. Rutherford reported the anomalies to McMurdo Operations via radio, receiving confirmation that other aircraft had experienced similar effects in the same region. The flight coordinator advised visual navigation and recommended he establish his position using recognizable terrain features rather than relying on instruments. The helicopter's other systems, engine monitors, altitude indicators, and communication equipment continued functioning normally, suggesting that the interference affected specifically magnetic and GPS-based navigation rather than producing general electromagnetic disruption. Rutherford completed his mission, delivering supplies to a field camp 30 kilometers short of the mountain's main peaks, noting that instruments returned to normal function during the return flight once distance from the range exceeded 35 kilometers. Ground surveys conducted over the following months attempted to characterize the magnetic anomaly's extent and intensity. Teams equipped with magnetometers traversed the accessible areas around the Fosdick Mountains, measuring field strength at intervals of 100 meters and recording variations from Earth's background magnetic field. The measurements revealed a roughly elliptical zone of intense magnetic disturbance centered on the mountain's southern peaks, extending approximately 70 kilometers along the range's axis and 40 kilometers perpendicular to it. Within this zone, magnetic field strength varied by more than 3,000 nanoteslers from baseline, fluctuations powerful enough to render standard compasses useless and sufficient to affect sensitive electronic navigation systems. Geological analysis of the mountains focused on identifying iron-rich formations or magnetized rock that might produce such intense fields. The Fosdick Mountains formed part of the Marie Birdland volcanic province, created through hotspot activity similar to processes that built the Hawaiian Islands. Volcanic rocks could retain strong magnetic signatures if they cooled in the presence of Earth's magnetic field, and subsequent geological processes could concentrate these magnetized formations into regions producing localized anomalies. Samples collected from accessible outcrops showed basaltic composition with magnetite content consistent with volcanic origin, but the concentrations measured could not account for the anomaly's intensity without requiring magnetite deposits far more extensive than surface geology suggested. Magnetic surveys from aircraft flying at various altitudes mapped the anomaly's three-dimensional structure, revealing that the disturbance's intensity decreased with altitude but remained detectable at heights exceeding 3,000 meters. This vertical profile indicated that the source extended deep into the crust rather than residing in near-surface formations, requiring a volume of magnetized rock or a concentration of magnetic minerals orders of magnitude larger than what volcanic processes typically produced. Calculations based on the field strength and geometry suggested a source region containing ferromagnetic material with magnetization levels approaching those of processed iron ore, rather than naturally occurring basalts. Attempts to explain the anomaly through conventional geological mechanisms encountered the problem of scale. Natural remanent magnetization in volcanic rocks could produce local anomalies measured in hundreds of nanoteslas, perhaps reaching 1,000 in exceptional cases where cooling conditions and mineral content aligned favorably. The Fosdick Mountains anomaly exceeded these values by factors of 3 to 5 across a region, encompassing thousands of cubic kilometers of crust. Even if the entire volume consisted of highly magnetized basalt, which surface sampling indicated it did not, the field strength remained higher than standard models predicted. Some researchers proposed that unique cooling conditions during the mountain's formation had produced unusually strong magnetization, perhaps through repeated volcanic episodes that added layers of strongly magnetized rock, or through interaction with an anomalously intense magnetic field present during crystallization. These scenarios required special circumstances beyond what geological evidence supported and failed to explain why the Fosdick Mountains showed such extreme magnetization, while neighboring volcanic formations in Marie Birdland displayed normal magnetic properties. Pilots transiting the region now plan routes that avoid the anomalous zone, or accept that instrument navigation will be unavailable for portions of their flight. The area appears on aeronautical charts, with special notations warning of magnetic disturbance and unreliable GPS, transforming a routine mountain range into a navigation hazard that requires old skills of pilotage and dead reckoning. The source of the anomaly remains unidentified, buried beneath ice and rock where direct sampling cannot reach, its nature revealed only through the invisible field that radiates upward to confound the instruments humans trust for orientation in the featureless Antarctic landscape. When NASA scientist Ralph von Freys analyzed the GRACE satellite gravity data for Wilkes Land in 2006, the readings showed a mass concentration larger than any impact crater on Earth, buried beneath 1.5 miles of ice, its density suggesting something that should not exist there. The Gravity Recovery and Climate Experiment satellites, launched in 2002, measured Earth's gravitational field with unprecedented precision by tracking minute variations in the distance between two orbiting spacecraft as they passed over regions of varying mass. Areas of higher density pulled the leading satellite slightly ahead, while lower density regions allowed the trailing satellite to catch up, and these tiny perturbations, measured to within microns, revealed the planet's internal structure with detail impossible to achieve through surface observations alone. The Wilkes Land anomaly appeared as a massive positive gravity signature centered at coordinates in the Australian Antarctic territory, approximately 600 kilometers inland from the coast. The signal indicated excess mass equivalent to a metallic asteroid more than 300 kilometers in diameter, concentrated in a roughly circular formation beneath the ice sheet. Von Frieser cross-referenced the gravity data with magnetic surveys conducted by aircraft in the 1990s, finding that the same region showed intense magnetic anomalies consistent with shocked rock and melted material, characteristics associated with hypervelocity impacts. The correlation between gravity and magnetic signatures suggested a single geological feature rather than coincidental overlapping formations. Impact crater modeling, based on the mass concentration and magnetic properties, indicated that if the feature represented an asteroid strike, the impacting body would have measured between 48 and 80 kilometers in diameter, depending on composition and impact velocity. Such an object striking Earth would release energy measured in millions of megatons, sufficient to trigger mass extinction events through immediate devastation and long-term climate disruption. The Chicxulub crater in Mexico, linked to the extinction of non-avian dinosaurs 66 million years ago, resulted from an impactor estimated at 10 to 15 kilometers across. The Wilkes Land feature suggested something 5 to 8 times larger, implying an impact of correspondingly greater magnitude. Dating the potential impact through direct sampling remained impossible given the ice coverage, but geological context provided constraints. The East Antarctic ice sheet began forming approximately 34 million years ago during the Eocene-Oligocene transition, when atmospheric carbon dioxide levels dropped and temperatures cooled sufficiently for permanent ice to accumulate. Any impact predating this period would show evidence in the geological record through iridium enrichment in sedimentary layers, shocked quartz dispersed globally, and extinctions corresponding to the event's timing. The fossil record showed a significant extinction event approximately 250 million years ago during the Permian-Triassic boundary, when more than 90% of marine species disappeared, though the cause of that extinction remained debated among paleontologists, with volcanic activity and ocean chemistry changes serving as leading explanations. Some researchers proposed that the Wilkes Land impact might have triggered the Permian-Triassic extinction, the energy release fracturing crust and initiating massive volcanic eruptions on the opposite side of the planet in what is now Siberia. This theory required the impact to have occurred at precisely the right location and with sufficient force to generate antipodal volcanism, a mechanism observed in computer simulations but difficult to confirm through geological evidence. The timing alignment between a hypothetical Wilkes Land impact and the Permian-Triassic boundary remained speculative without direct dating of the anomalous mass. Alternative explanations for the gravity signature struggled to match the observed characteristics. Subglacial mountain ranges could produce positive gravity anomalies if they contained unusually dense rock, but the Wilkes Land region showed relatively flat bedrock topography in radar surveys, lacking the elevation variations that would accompany a major mountain system. Volcanic intrusions might concentrate dense material at depth, yet the circular geometry and scale of the anomaly exceeded what volcanic processes typically produced. Mantle upwellings could bring dense material closer to the surface, but these features generally showed elongated rather than circular shapes and occurred along plate boundaries rather than in cratonic interiors. The hypothesis that attracted both interest and skepticism suggested that the mass concentration might not be impact-related at all, but instead represented something deposited or constructed before ice sheet formation. This explanation required invoking processes outside standard geology, proposing that the buried feature possessed characteristics inconsistent with natural formation. The gravity signature's intensity implied metallic composition or material denser than typical crustal rock, and the circular arrangement suggested organization rather than random distribution. Proponents of this interpretation pointed to the feature's size and regularity as evidence that natural impact or volcanic processes could not fully account for observations, while critics noted that extraordinary claims required extraordinary evidence and that ice coverage prevented obtaining such evidence. Drilling through 2,500 meters of ice to sample the anomaly directly would require funding and logistical support beyond current Antarctic research capabilities, and even if drilling succeeded, the sample area would represent a minute fraction of the feature's total extent, potentially missing key characteristics. Seismic surveys could provide additional structural information, but offered limited ability to determine composition or origin. The feature remained interpretable only through gravitational and magnetic measurements, indirect observations that constrained possibilities without definitively identifying what lay beneath the ice. The mass beneath Wilkes Land continues to appear in satellite gravity maps as a prominent anomaly, its presence undeniable, its nature uncertain. Conferences examining major impact structures include presentations debating whether the feature represents the largest crater on Earth or something requiring alternative explanation, discussions that remain unresolved for lack of direct evidence. The ice sheet preserves whatever lies below while preventing the investigation that might settle questions about its origin, leaving the anomaly suspended between scientific categories, too large and too strange to ignore, too inaccessible to examine. Seismic surveys mapping the bedrock beneath East Antarctica's ice sheet in 2008 revealed peaks rising 9,000 feet above the hidden landscape, and geologist Fausto Ferraccioli faced an impossibility: a mountain range as large as the Alps, existing in the center of a billion-year-old stable craton where no mountains should form. The Gamburtsev Mountains, named after a Soviet geophysicist who first detected hints of their existence in the 1950s through gravimetric measurements, occupied a region of East Antarctica that geological theory classified as tectonically dead. Cratons, the ancient stable cores of continents, consisted of thick, rigid crust that had not experienced significant deformation for hundreds of millions of years. Their mountain-building episodes completed in the deep geological past, and their elevated terrain long since eroded to gentle plains. The discovery that a mountain range comparable to the European Alps existed beneath the ice challenged fundamental assumptions about how mountains form and persist. The seismic data, collected through arrays of sensors recording echoes from the explosive charges detonated on the ice surface, mapped a range extending more than 1,200 kilometers in length, with individual peaks exceeding 2,700 meters in elevation above the surrounding bedrock. The mountains showed the characteristic steep-sided valleys and sharp ridges of young, actively forming ranges rather than the rounded, weathered profiles expected from ancient formations. Their topography resembled the Alps or the Rockies in their current state, not the eroded remnants that billion-year-old mountains should have become. Mountain formation required tectonic forces to uplift crust, processes associated with plate collisions, volcanic activity, or rifting events that produced compression or extension in Earth's crust. The Gamburtsev Mountains lay more than 1,000 kilometers from the nearest plate boundary, positioned in the interior of the East Antarctic Craton, where the crust had remained stable since the Precambrian era. Seismic tomography showed no evidence of active tectonics beneath the range, no subducting slabs or mantle plumes that might drive uplift. The crust appeared cold and rigid, lacking the heat and deformation that characterized regions of active mountain building. Dating the mountain's formation proved difficult without rock samples, but the ice covering them provided indirect constraints. Ice cores from the region and climate modeling indicated that the East Antarctic ice sheet had covered the Gamburtsev Mountains for at least 14 million years, possibly much longer. During this period, the ice had flowed over and around the peaks, its movement controlled by the underlying topography. The mountains had stood high enough to affect ice flow patterns throughout the ice sheet's existence, indicating that their elevation predated glaciation and had been maintained despite millions of years of ice loading and erosion. The persistence of such high relief posed a separate problem from the mountain's initial formation. Erosion worked continuously to reduce elevated terrain, weathering, breaking down rock, and removing material that rivers and glaciers carried away. Mountains left exposed to erosional processes for tens of millions of years typically diminish to low hills or flat plains, their substance scattered across surrounding lowlands. The Gamburtsev Mountains showed morphology suggesting minimal erosion since their uplift, their steep faces and sharp peaks inconsistent with prolonged weathering. The ice that covered them should have accelerated rather than prevented erosion, glacial flow grinding against bedrock and plucking away weakened material. Yet the range maintained elevations and relief that appeared geologically recent. Several hypotheses attempted to reconcile observations with geological principles. One proposal suggested that the mountains formed during the Precambrian through tectonic collision and had somehow avoided erosion through unique climatic conditions that kept them frozen before the current ice sheet formed. This theory required the mountains to have been preserved in a frozen state for hundreds of millions of years, a scenario that climate models indicated was implausible given the thermal evolution of the Antarctic continent. Even if early glaciation had protected the range, periods of warmer climate should have exposed peaks to erosion and reduced their relief substantially. Another explanation proposed that the mountains were being actively uplifted through processes not yet detected by seismic monitoring, perhaps through slow isostatic rebound following removal of dense lower crust, or through thermal expansion of the upper mantle. These mechanisms could produce gradual uplift without obvious seismic signatures, though they typically operated at rates of millimeters per year, slow enough that erosion under an ice sheet should still dominate over geological time. Calculations indicated that uplift rates would need to exceed 5 millimeters annually to maintain the observed topography against glacial erosion, rates higher than isostatic processes normally produced. A more radical hypothesis suggested that the ice sheet itself somehow preserved or even enhanced the mountain's relief through mechanisms not fully understood. Ice flow could remove weathered material from valley floors while protecting ridge crests, potentially sharpening topography rather than subduing it. Computer simulations of ice-bedrock interaction showed that under certain conditions, glacial erosion could maintain steep topography, though these conditions required specific ice flow patterns and bedrock properties that may or may not exist beneath the Gamburtsev range. The hypothesis remained speculative, untested against the actual conditions present at the site. The mountains stand beneath their ice cover, invisible to surface observation, but mapped in increasing detail by successive geophysical surveys. Each new dataset refines understanding of their dimensions and morphology while deepening the mystery of their existence. For geologists who study the data, the Gamburtsev Mountains represent either an extraordinary example of geological processes operating in ways theory has not yet characterized, or evidence that fundamental assumptions about mountain building and erosion may require revision when applied to environments as extreme and poorly understood as subglacial Antarctica. Atmospheric scientist Dr. Michel Torres watched the satellite data from September 15, 2019 in disbelief as the Antarctic ozone hole, which her models predicted would expand uniformly, instead contracted by 40% in 72 hours, before expanding again in a different location. Behavior no atmospheric model could explain. The ozone hole above Antarctica had been discovered in 1985, its formation linked to chlorofluorocarbons released by human industrial activity that accumulated in the stratosphere and catalyzed ozone destruction during the Antarctic spring. Understanding of the phenomenon had improved steadily over subsequent decades. Atmospheric chemistry models incorporating the reactions between chlorine compounds, ozone molecules, and polar stratospheric clouds that provided surfaces for the destructive reactions to occur. By 2019, scientists could predict the ozone hole's general characteristics with reasonable confidence based on temperature patterns, chlorine concentrations, and the timing of the polar vortex that isolated Antarctic air masses from the global atmosphere. Models anticipated gradual expansion as spring progressed and temperatures in the stratosphere remained cold enough to maintain the polar vortex, followed by breakdown of the vortex in late spring, when warming air disrupted the circulation pattern and allowed ozone-rich air from lower latitudes to flow southward. The predictable cycle had repeated annually, with minor variations that models attributed to natural climate fluctuations affecting temperature and wind patterns. Torres had been monitoring the 2019 ozone hole through satellite data provided by NASA's Aura spacecraft and the European Space Agency's Sentinel satellites, both equipped with instruments measuring stratospheric ozone concentrations with high spatial and temporal resolution. Initial observations in August showed the hole forming as expected, its area expanding from 0 in mid-August to approximately 15 million square kilometers by early September, dimensions consistent with model predictions based on that year's meteorological conditions. The models forecast continued expansion through late September, reaching a maximum area of roughly 22 million square kilometers before beginning gradual contraction in October. The actual behavior departed dramatically from predictions on September 15th, when satellite observations showed the ozone hole's area decreasing rapidly, shrinking by more than 6 million square kilometers over 3 days. Simultaneously, ozone concentrations increased within the affected region, rising from near zero to values approaching 50 Dobson units, levels that indicated substantial ozone influx from surrounding air masses. The contraction occurred without corresponding changes in stratospheric temperature or wind patterns that might explain breakdown of the polar vortex, and the vortex's circulation remained strong according to meteorological analyses. By September 18th, the hole had stabilized at its reduced size, then began expanding again on September 20th, growing toward the southeast rather than uniformly in all directions as thermal and dynamic processes should produce. Temperature measurements throughout the episode showed the stratosphere above Antarctica remained cold enough to support ozone destruction, with values between -78 and -82 degrees Celsius, well below the threshold of -78 degrees required for polar stratospheric cloud formation. Chlorine activation should have continued unabated under these conditions, yet ozone concentrations increased despite the presence of active chlorine compounds. Chemical transport models attempting to reproduce the observations failed, producing either continued ozone depletion or requiring artificial adjustments to wind fields that had no basis in measured meteorology. The 2019 anomaly was not isolated. Examination of historical satellite data revealed similar events in 2002, 2012, and 2017, years when the ozone hole had exhibited rapid contractions or unexpected movements that models had attributed at the time to unusual meteorological conditions. Detailed reanalysis showed that in each case, the meteorological conditions invoked to explain the behavior were themselves poorly understood deviations from normal patterns, essentially replacing one mystery with another. The ozone hole appeared to respond to forcing mechanisms that atmospheric science had not identified or could not properly characterize with existing observations. Theories proposed to explain the anomalous behavior ranged from inadequate representation of small-scale mixing processes in models to possible effects of gravity waves generated by flow-over Antarctic topography that might episodically inject ozone-rich air into the polar vortex. None of these explanations could account for the rapidity of the observed changes or the pattern of contraction followed by asymmetric re-expansion. The mixing processes required to transport sufficient ozone into the vortex within 72 hours would need to be far more efficient than any mechanism atmospheric dynamics could support, and gravity wave effects typically operated on smaller spatial scales than the whole-wide changes observed. Some researchers suggested that changes in solar radiation reaching the stratosphere through variations in cloud cover or atmospheric particulates might affect ozone chemistry in ways current models did not capture, but measurements of incoming solar radiation showed no unusual variations during the anomalous periods. Others proposed that volcanic aerosols or other particulates might alter the surface area available for chlorine activation reactions, though no significant volcanic eruptions had occurred before the observed events, and aerosol measurements remained within normal ranges. Each Antarctic spring brings new predictions for the ozone hole's development, and each year the actual behavior includes elements that models fail to anticipate. The deviations sometimes favor smaller holes and faster recovery, occasionally producing larger and more persistent depletion than forecast. The accumulation of unpredicted events has not revealed underlying patterns that might improve models, but has instead highlighted how incompletely science understands the atmospheric processes governing ozone distribution above Antarctica, despite decades of intensive study and continuous satellite monitoring. Volcanologist Maria Sanchez lowered the temperature probe into the steaming waters of Deception Island's caldera on March 3, 2013, expecting readings consistent with shallow volcanic heat, but the thermometer registered 140 degrees Celsius at a depth where the temperature should have begun cooling, suggesting a heat source far below any known magma chamber. Deception Island, a horseshoe-shaped landmass in the South Shetland Islands, approximately 120 kilometers north of the Antarctic Peninsula, formed through volcanic activity that created a flooded caldera measuring roughly 12 kilometers across. The island's most recent eruptions occurred in 1967, 1969, and 1970, events that destroyed research stations and demonstrated the volcano's continued activity, though seismic monitoring since then had detected no signs of imminent eruption. Geothermal systems associated with active volcanoes typically showed predictable temperature profiles, heat declining with depth below the surface or water body as distance from the magma chamber increased. Shallow measurements near fumaroles or hot springs could reach boiling temperatures, but at greater depths, particularly in water-filled calderas where circulation distributed heat, temperatures should stabilize at values reflecting the balance between geothermal input and heat loss to the surrounding environment. Sanchez had measured temperatures at Deception Island's Port Foster, the flooded interior of the caldera, on previous expeditions, documenting surface temperatures between 30 and 70 degrees Celsius, depending on proximity to known thermal vents, and finding that temperatures decreased predictably with depth. The 2013 measurements departed from this pattern, beginning at approximately 40 meters depth, where the probe registered 95 degrees Celsius rather than the expected 60 to 70 degrees. Continued descent showed temperatures rising rather than falling, reaching 120 degrees at 60 meters and maintaining values above 135 degrees from 80 meters to the probe's maximum deployment depth of 120 meters. The temperature profile inverted the normal geothermal gradient, suggesting that the heat source lay deeper than any volcanic system should extend beneath the relatively thin oceanic crust supporting the South Shetland Islands. Seismic reflection surveys conducted as part of the same research program mapped the subsurface structure beneath Port Foster, identifying a magma chamber at approximately 3 to 4 kilometers depth, consistent with the shallow magma storage typical of caldera systems. The chamber's estimated volume and temperature, based on seismic velocities and attenuation of shear waves, indicated partially molten rock at temperatures between 900 and 1100 degrees Celsius, values normal for basaltic magma systems. Heat flow calculations using the magma chamber's properties predicted surface heat flux of approximately 800 milliwatts per square meter, elevated compared to normal oceanic crust, but insufficient to maintain the observed water temperatures at depth unless circulation patterns concentrated heat in specific locations. Thermal modelling attempted to reproduce the observed temperature profile by varying parameters, including magma chamber depth, size, temperature, and the permeability of overlying rock that controlled how efficiently heat reached the surface. No combination of geologically plausible parameters produced temperatures matching measurements. To generate 140-degree water at 120 meters depth required either a much shallower magma chamber than seismic data indicated, heat sources extending far below the primary chamber into the upper mantle, or hydrothermal circulation through highly fractured rock that delivered heat with exceptional efficiency. The first option contradicted seismic observations. The second required volcanic plumbing extending to depths unusual for island arc volcanism, and the third demanded rock permeability values at the extreme upper limit of measurements from other geothermal systems. Additional measurements at different locations within the caldera revealed that the anomalous temperatures occurred across a roughly circular region, 3 kilometers in diameter, centered on the caldera's geometric center. Outside this zone, temperature profiles returned to normal patterns with decreasing heat at depth. The boundary between normal and anomalous regions appeared relatively sharp, transitioning over horizontal distances of less than 200 meters, suggesting a localized heat source rather than broad regional effects. The heat output from the anomalous zone, calculated by integrating temperature measurements and estimating water circulation rates, totaled approximately 50 megawatts, equivalent to a small power plant and substantially exceeding what the mapped magma chamber should produce unless its properties differed significantly from seismic interpretations. Gas samples collected from thermal vents within the anomalous zone showed helium isotope ratios indicating mantle-derived volatiles, confirming connection to deep magmatic sources, but the isotope compositions did not differ substantially from samples collected outside the anomalous region. Carbon dioxide and sulfur dioxide concentrations remained within ranges typical of basaltic volcanism, providing no chemical signature that might explain the excess heat. The gases carried no unusual components that might indicate deeper or hotter sources than those feeding normal geothermal activity elsewhere on the island. Chilean and British research stations on Deception Island monitor the thermal activity continuously, maintaining temperature sensors at various depths and tracking changes that might herald renewed volcanic unrest. The anomalous heat zone has persisted without substantial variation since its documentation in 2013, neither expanding nor contracting significantly, its temperatures fluctuating only within the ranges expected from tidal influences on water circulation. Seismic activity beneath the caldera continues at low background levels, producing small earthquakes consistent with magma movement and geothermal fluid circulation, but showing no indication of magma rising toward the surface or sudden changes in the volcanic system's behavior. The source of the anomalous heat remains unidentified, buried too deep for direct sampling and obscured by the complex structure of a flooded volcanic caldera. Whether the heat reflects unusual magma chamber geometry that seismic methods have incompletely characterized, hydrothermal circulation through rock structures that concentrate heat beyond normal efficiency, or processes that volcanic models have not adequately considered, it continues to defy quantitative explanation while maintaining its presence as a measurable, persistent feature of Deception Island's geothermal system. The seismograph at Roosevelt Island recorded a movement beginning at 4:23 a.m. on July 7, 2017, a slow, massive displacement of something beneath the Ross Ice Shelf, taking 6 hours to complete a shift of 300 meters, moving at a speed that matched neither ice flow nor any known geological process. Roosevelt Island, a dome of grounded ice rising from the Ross Ice Shelf, approximately 160 kilometers from the shelf's seaward edge, hosted a seismic monitoring station installed in 2014 as part of a project studying ice dynamics and crustal structure beneath West Antarctica. The network of seismometers detected earthquakes, ice quakes produced by fracturing within the ice sheet, and the subtle signals generated by glacial movement, providing researchers with continuous data on processes affecting the region's stability. Seismologist Dr. Robert Chen reviewed the recordings from that morning, initially assuming the signals represented ice movement or perhaps a distant earthquake whose waves had propagated through the crust. Ice shelves generated characteristic seismic signatures as they flexed with tidal forces, grounded sections scraped against bedrock, and crevasses opened or closed under stress. These signals typically appeared as brief bursts of energy lasting seconds to minutes, their frequency content and waveform shapes allowing identification of the source mechanism. The July 7th event differed fundamentally from any ice-related signal in Chen's experience. The movement began gradually, seismic amplitude increasing over approximately 15 minutes until reaching a steady level it maintained for the next 5 hours and 45 minutes before declining back to background over another 15-minute period. The waveforms showed characteristics of sliding or displacement rather than sudden rupture. The signal dominated by low frequencies below 3 Hz that suggested massive objects moving slowly rather than rapid crack propagation. Triangulation using multiple seismometers indicated that the source lay directly beneath the ice shelf, at depths between 15 and 30 kilometers, placing it in the upper mantle or lowermost crust far below the ice bedrock interface. Earthquake activity in this region should be minimal given the tectonic setting. The Ross Ice Shelf rested on continental crust that had been stable for hundreds of millions of years, far from active plate boundaries, and without the stress accumulation that generated earthquakes in tectonically active zones. Occasional seismic events occurred, typically small earthquakes with magnitudes below 3.0 triggered by ice loading changes or residual stresses in the crust, but these events lasted seconds and showed the sharp onset characteristic of brittle fracture. The 6-hour duration and gradual evolution of the July 7th movement matched no earthquake mechanism. Ice flow offered an alternative explanation, but calculations quickly ruled it out. The Ross Ice Shelf moved toward the Ross Sea at velocities between 400 and 800 meters per year, depending on location, translating to roughly 1 to 2 meters per day. The detected movement speed, 300 meters over 6 hours, exceeded ice flow rates by factors of 100 or more, and occurred at depths where ice did not exist. Basal sliding, the process by which ice sheets moved over bedrock, generated seismic signals at the ice rock interface approximately 1 kilometer below the surface, not at mantle depths, and produced different frequency characteristics than the observed event. Additional occurrences of similar movements appeared in the seismic record over subsequent months, 13 separate events detected through November 2017, each lasting between 4 and 9 hours and showing displacement distances from 200 to 500 meters. The events clustered temporally, with intervals between occurrences ranging from 8 to 18 days, showing no obvious periodicity that might link them to tidal forces, seasonal changes, or other cyclical processes. The source location varied slightly among events, shifting across a region approximately 50 kilometers in diameter centered beneath the ice shelf's interior, but always occurring at similar depths in the 15 to 30 kilometre range. Chen coordinated with other Antarctic seismic networks to determine whether the movements appeared on distant stations, finding that sensors more than 300 kilometres from Roosevelt Island detected no signals corresponding to the events. This localization indicated relatively small magnitude movements despite their long duration, suggesting that whatever was displacing involved slow slip across limited areas rather than rupture across large fault surfaces. Moment calculations based on seismic amplitude and duration indicated equivalent earthquake magnitudes between 4.5 and 5.2, substantial but not extraordinary. Yet the 6-hour time frame made these unlike any earthquake sequence on record. Glaciologists and geophysicists examining the data proposed various mechanisms. Some suggested slow slip events similar to those observed along certain subduction zones where fault surfaces slipped gradually rather than in sudden earthquakes, but the Ross ice shelf region lacked the tectonic setting where such events typically occurred. Others proposed that mantle flow or lower crustal deformation might generate the observed signals, though the timescales seemed too short for convective processes and too long for elastic deformation. The movements appeared too organized to represent random thermal or mechanical adjustments in the crust. The pattern continued through 2018 and 2019, with decreasing frequency, the final detected event occurring in March 2020. Analysis of the complete sequence revealed subtle patterns in timing and location, suggesting that the events progressed spatially, each movement occurring slightly offset from the previous one, as though something were migrating slowly beneath the ice shelf. The progression showed no clear directionality, the path wandering rather than following a systematic route, and the sequence terminated without obvious cause. The seismic record returning to normal background activity that has persisted since. What moved beneath the Ross ice shelf during those 3 years remains unidentified, its depth placing it beyond direct observation, and its characteristics matching no process that geophysics has adequately characterized. The seismic records document its passage without revealing its nature, leaving questions about whether the movements represented geological processes operating in ways current understanding cannot predict, or something outside the framework of conventional Earth science entirely. Meteorologist David Park photographed the polar stratospheric clouds over Halley Station on June 18, 2011, capturing their characteristic iridescence, but the images revealed something unprecedented. The clouds had arranged themselves into hexagonal patterns with geometric precision, each hexagon exactly 2.3 kilometers across. Polar stratospheric clouds, also called nacreous clouds, for their mother-of-pearl appearance, formed at altitudes between 15 and 25 kilometers when temperatures in the Antarctic stratosphere dropped below -78 degrees Celsius. At these extreme temperatures, trace amounts of water vapor and nitric acid condensed into ice crystals that diffracted sunlight, creating the brilliant colors that made the clouds visible even during the perpetual darkness of Antarctic winter, when the sun remained below the horizon, but its rays still illuminated the high atmosphere. The clouds appeared regularly each Antarctic winter, their formation well understood as a consequence of the polar vortex that isolated Antarctic air and allowed stratospheric temperatures to plunge far below freezing. Meteorologists had photographed and studied these clouds for decades, documenting their optical properties, chemical composition, and role in ozone depletion chemistry. The clouds typically showed irregular shapes, wispy filaments, and patches of colour that varied with viewing angle and solar illumination, their forms reflecting the chaotic turbulence of stratospheric winds and the random nucleation of ice crystals. Park had observed and photographed hundreds of nacreous cloud displays during his 3 winter seasons at Halley, none of which had shown anything resembling organized geometric structure. The hexagonal arrangement appeared across the entire visible extent of the cloud field, approximately 80 kilometers from edge to edge, with individual hexagons maintaining consistent size to within measurement error of the photographic analysis. Park used multiple images taken from slightly different positions to establish the three-dimensional structure of the pattern, finding that the hexagons existed not as a flat array, but as a honeycomb structure, extending vertically through several kilometers of altitude. Each cell measured 2.3 kilometers in horizontal extent and approximately 1.8 kilometers in vertical dimension, the proportions showing a ratio close to the square root of 2, a relationship that appeared repeatedly in close-packed geometric structures, but which atmospheric processes had no mechanism to produce. Subsequent observations over the following weeks revealed that the geometric patterns persisted across multiple cloud formation events, appearing on June 23rd, July 2nd, July 9th, and July 17th, each time showing hexagonal organization, with cell sizes varying by less than 5% from the initial 2.3 kilometer measurement. The patterns lasted for hours once formed, slowly degrading as stratospheric winds sheared the cloud structure, but maintaining recognizable hexagonal form far longer than atmospheric turbulence should allow. Computer simulations of cloud formation and evolution, incorporating measured wind speeds, temperature profiles, and crystal nucleation rates, produced irregular cloud fields that bore no resemblance to the observed geometry. Analysis of the pattern's mathematical properties revealed additional strangeness beyond simple hexagonal packing. The cell boundaries aligned with consistent orientation. All hexagons rotated to the same angle relative to geographic north within 2 degrees of accuracy. This alignment suggested organization on scales exceeding individual hexagons, as though the entire cloud field responded to some forcing mechanism that imposed both local structure and global coordination. Atmospheric dynamics operated through processes like gravity waves, convection, and wind shear that could produce regular patterns in some circumstances, but these mechanisms typically generated wave-like structures, with characteristic scales determined by atmospheric stability and wind speed, not precise geometric cells. Temperature measurements throughout the stratosphere during pattern formation. Events showed no unusual variations that might explain organized convection or wave activity. The stratosphere remained stably stratified, temperature increasing with altitude in a manner that suppressed vertical motion and prevented the convective overturning that might organize clouds into cells. Humidity remained uniformly low, providing no gradient that might drive differential ice crystal formation. Wind measurements showed the typical laminar flow of the polar vortex, steady circulation around Antarctica without the velocity variations or directional changes that might impose structure on cloud fields. Some atmospheric physicists suggested that acoustic waves or electromagnetic phenomena might organize ice crystal nucleation, creating patterns through resonance effects or electromagnetic field interactions. But measurements of acoustic energy and electromagnetic field strength in the stratosphere showed no unusual activity during pattern formation. The energy required to organize crystals across 80 kilometers of atmosphere would need sources that monitoring equipment should detect, yet no anomalous signals appeared in any observational dataset. The patterns continue to appear each Antarctic winter, documented by researchers at Halley Station and other Antarctic facilities where polar stratospheric clouds are visible. Each occurrence provides additional data on cell dimensions, alignment, and duration. The accumulated observations confirming that the phenomenon repeats reliably while offering no insight into the mechanism responsible. The hexagons form, persist, and dissipate according to schedules that correlate with stratospheric temperature, but not with any identified organizing force, leaving atmospheric science to catalogue a pattern it can measure precisely but cannot explain. Particle physicist Dr. James Wu reviewed the IceCube detector data from December 3, 2016, searching for cosmic neutrino signatures, when he found traces of particle interactions that matched no known physics, energy signatures appearing from below the detector. Impossible unless particles were traveling upward through the Earth itself. The IceCube Neutrino Observatory, buried in a cubic kilometre of Antarctic ice beneath the Amundsen-Scott South Pole Station, consisted of more than 5,000 optical sensors strung along 86 cables descending to depths of 2,450 metres. The sensors detected Cherenkov radiation, the faint blue glow produced when charged particles moved through ice faster than light speed in that medium, a phenomenon that occurred when neutrinos interacted with ice nuclei and created cascades of secondary particles. Neutrinos, nearly massless particles that interacted only through the weak nuclear force, passed through ordinary matter almost without resistance. Trillions of neutrinos from the Sun streamed through Earth every second, most traversing the entire planet without a single interaction. The IceCube detector's vast volume increased the probability of catching occasional neutrino events, recording roughly 300 interactions per year from cosmic sources beyond the solar system. These events appeared as flashes of light when neutrinos struck ice molecules, their direction determined by the geometry of sensors that detected the Cherenkov cone, and their energy calculated from the intensity and pattern of light emission. Standard model physics predicted that cosmic neutrinos should arrive from all directions, coming from supernova remnants, active galactic nuclei, and other high-energy astrophysical sources scattered across the universe. The detector recorded events originating from above, photons traveling downward from interactions occurring in the ice, and events from the horizon where neutrinos pass through minimal amounts of matter before reaching the detector. Downward traveling neutrinos from below, requiring passage through Earth's entire diameter, should be absorbed or scattered at a rate determined by their interaction cross-section, with only the highest energy neutrinos capable of penetrating the planet. The December 3rd events showed particles arriving from below at energies between 15 and 40 tera-electron volts, a range where Earth should be effectively opaque to neutrino passage. Wu examined the event reconstructions multiple times, verifying that the algorithms correctly identified particle direction from the timing patterns of sensor triggers. The Cherenkov light cone pointed unambiguously upward, indicating particles moving from deep within Earth toward the surface. Energy calculations based on the light intensity showed values inconsistent with the few neutrino flavors that could traverse Earth at these energies. The detected events carrying insufficient energy for transmission through the planet, yet too much energy to be misidentified atmospheric neutrinos produced by cosmic ray interactions in the atmosphere above the detector. Additional anomalous events accumulated over subsequent months, 23 separate detections through June 2017 showing similar characteristics. The events appeared randomly in time, showing no correlation with known astrophysical transients or solar activity. Their energy spectrum differed from both atmospheric and cosmic neutrino distributions, clustering in a narrow range rather than following the power law decrease typical of high-energy particle sources. Attempts to identify a common source region for the upward-traveling particles found no concentration. The events arriving from different directions across the southern sky as though produced by multiple sources or by processes occurring throughout Earth's interior. Theoretical physicists examining the data proposed several explanations, none entirely satisfactory. Some suggested the signatures represented previously unknown neutrino interaction modes that allowed passage through Earth with lower absorption than standard model calculations predicted, requiring extensions to particle physics that had no independent experimental support. Others proposed that the particles were not neutrinos, but some other weakly interacting species that current theory did not include hypothetical particles that would require substantial modifications to the standard model structure and might have been produced in the early universe or in extreme astrophysical environments. Instrumental explanations face difficulties accounting for the consistency of the anomalous signatures across multiple independent events and the clear directionality indicated by timing patterns that the detector had been specifically designed to measure accurately. Systematic errors typically produced random noise or consistent biases that affected all events similarly, not discrete, well-reconstructed events with properties differing from both signal and background expectations. The IceCube collaboration conducted extensive checks of sensor calibration, timing systems, and reconstruction algorithms, finding no technical faults that might generate spurious, upward-traveling events. A more exotic possibility suggested that the particles might represent decay products from dark matter interactions occurring within Earth, hypothetical, weakly interacting massive particles capturing in the planet's gravitational field and accumulating in the core where their annihilation might produce detectable secondary particles. This explanation required dark matter to possess properties beyond minimal theoretical frameworks and predicted additional signatures in other detectors that had not been observed, leaving it as speculation without independent verification. The anomalous signatures continue appearing at IceCube at a rate of roughly one event per month, their properties remaining consistent with initial observations while their origin remains completely unidentified. Each detection is catalogued, analysed for patterns that might reveal commonalities pointing toward a source or mechanism, and compared with data from other neutrino observatories worldwide that have reported no similar events, suggesting that if real, the phenomenon is either localized to the Antarctic ice or requires the specific detector configuration that IceCube provides. For particle physicists, the events represent either mundane instrumental artifacts yet to be identified, or the first hints of physics beyond the standard model, particles traversing Earth through mechanisms that require new understanding of how matter and energy behave at fundamental levels. Geologist Dr. Susan Mitchell examined the rock face in the Queen Maud Mountains on January 15, 2009, where Cambrian-era shale from 500 million years ago lay directly against Jurassic sandstone from 180 million years ago, with no transitional layers, no fault lines, no explanation for the missing 320 million years of geological time. Mitchell had worked in Antarctic geology for 12 years, conducting field surveys across the Transantarctic mountains and documenting the region's complex tectonic history through careful mapping of rock formations and their structural relationships. The standard principles of stratigraphy held that younger rocks overlay older rocks in continuous sequences unless disrupted by faulting, erosion, or other identifiable processes, each of which left characteristic signatures that trained geologists could recognize. The contact between the two formations appeared as a sharp boundary, visible as a distinct line where grey Cambrian shale met red-brown Jurassic sandstone. Mitchell collected samples from both sides of the contact, examining them under magnification for evidence of weathering surfaces, soil development, or other features that would indicate a time gap between deposition. The Cambrian shale showed no signs of surface exposure, its uppermost layers containing the same marine fossils and fine-grained texture as material deeper in the formation. The Jurassic sandstone showed no basal conglomerate or erosional features at its base, characteristics that typically marked unconformities where significant time gaps separated depositional episodes. Radiometric dating of minerals from both formations confirmed their ages with precision that left no room for measurement error. Zircon crystals extracted from volcanic ash layers within the Cambrian shale yielded uranium-lead ages of 505 million years, while similar analysis of the Jurassic sandstone produced ages of 178 million years. The 327 million year gap represented by these dates should have included the entire Ordovician, Silurian, Devonian, Carboniferous, and Permian periods, each of which typically left distinct rock sequences in regions with continuous sedimentation. The absence of these intervening periods would be remarkable anywhere, but the lack of erosional surfaces or structural disruption at the contact made it geologically inexplicable. Mitchell expanded her investigation to other locations along the Transantarctic mountains, finding similar impossible contacts at 7 additional sites scattered across more than 800 kilometers of the mountain range. Each location showed the same pattern: older rocks in direct contact with much younger rocks, time gaps ranging from 200 to 400 million years, and no physical evidence of the processes that should have created unconformities. The consistency across multiple sites argued against local explanations involving unusual preservation or erosion patterns and suggested a regional phenomenon affecting the entire mountain system. Structural analysis searched for thrust faults that might have placed older rocks atop younger formations, a process that could explain anomalous contacts through tectonic stacking rather than missing time. Thrust faulting commonly occurred in mountain belts, where convergent tectonics compressed crust and drove older rocks up and over younger ones along low-angle fault surfaces. Such faults displayed characteristic features, including crushed rock along the fault plane, folding in adjacent layers, and systematic orientation of the fault surface relative to regional tectonic stress. Mitchell found none of these indicators. The contacts appeared as simple bedding planes, horizontal or gently dipping surfaces that showed no deformation or disturbance. The missing time intervals corresponded to periods of significant biological and environmental change in Earth's history. The Devonian period saw the evolution and diversification of fish. The Carboniferous witnessed the formation of vast coal swamps and the rise of reptiles, and the Permian ended with the largest mass extinction in the geological record. Rock sequences from these periods existed elsewhere in Antarctica and on other continents, preserving fossils and chemical signatures that documented these transformations. The Transantarctic mountains should have recorded these events if the region had remained above sea level or accumulated sediments in marine environments, yet the rock record jumped directly from Cambrian marine shales to Jurassic desert sandstones, as though the intervening 320 million years had simply not occurred. Some geologists proposed that the region had been elevated above sea level during the missing time interval, and that erosion had removed all deposited sediments before Jurassic deposition began. This hypothesis required explaining why erosion would remove hundreds of millions of years' worth of rock without leaving any unconformity surface. No weathered zone where ancient soils developed. No angular discordance between underlying and overlying strata. Erosional unconformities typically showed clear evidence of the time gap they represented. Surfaces that could be traced and mapped across regions. The Transantarctic contacts showed no such features. Others suggested that the missing intervals represented times when no deposition occurred, the region existing as a stable landmass that neither accumulated nor lost material. This explanation faced the problem that 320 million years of complete stability, with neither deposition nor erosion, had no precedent in the geological record. Even the most stable continental interiors showed evidence of occasional marine incursions, river system development, or soil formation over such vast time spans. The hypothesis required conditions so unusual that it essentially replaced one mystery with another. The impossible contacts remain exposed in the Transantarctic mountains, documented in geological maps and stratigraphic columns that show the time gaps without explaining them. Each field season brings additional surveys as researchers attempt to find locations where the missing intervals might be preserved or where evidence of their removal might be detected, but the pattern persists unchanged. Somewhere in the history of these mountains, more than 300 million years of Earth's story disappeared, leaving rocks from distant eras pressed together as though the intervening time had never existed or had been extracted from the sequence through processes that left no mark of their passage. Microbiologist Dr. Rachel Kim analysed the bacterial samples retrieved from Lake Mercer in January 2019, expecting ancient, isolated life forms adapted to extreme conditions, but the genetic sequencing revealed DNA markers identical to deep-sea species from oceans thousands of miles away, suggesting contact that should be impossible. Lake Mercer, located beneath the West Antarctic ice sheet, approximately 600 kilometers from the Ross Sea, had been sealed from the surface for an estimated million years, according to ice core chronology and glacial modelling. The drilling project that reached the lake required extraordinary contamination protocols, using heated water and ultraviolet sterilization to ensure that samples collected from the subglacial environment contained only organisms native to that isolated ecosystem, rather than surface microbes introduced during drilling operations. The lake occupied a depression in bedrock approximately 15 kilometers long and 8 kilometers wide, filled with liquid water maintained above freezing by geothermal heat from below and insulated by more than 1,000 meters of overlying ice. Temperature measurements showed the water at 0.5 degrees Celsius, cold but liquid, with chemistry indicating high concentrations of dissolved minerals that had accumulated over millennia of bedrock weathering. The environment represented an extreme habitat, perpetually dark, cold and isolated from atmospheric exchange or photosynthetic food webs. Any organisms surviving in such conditions would necessarily be adapted to chemosynthetic metabolism, extracting energy from chemical reactions involving minerals dissolved in the water rather than relying on sunlight-derived organic compounds. Initial microscopy confirmed the presence of bacterial cells in concentrations of about approximately 10,000 per milliliter, sparse compared to surface waters, but substantial for such an extreme environment. The cells showed morphologies consistent with common bacterial forms, rods and cocci that could belong to numerous taxonomic groups. Culture attempts in the laboratory produced limited growth, the organisms proving difficult to maintain outside their native conditions, but sufficient biomass was obtained for DNA extraction and sequencing. The genetic analysis began with amplification of ribosomal RNA genes, conserved sequences used to identify bacterial lineages and construct evolutionary relationships. The sequences revealed organisms belonging to multiple bacterial phyla, including Proteobacteria, Actinobacteria, and Bacteroidetes, classifications that contain thousands of known species from diverse environments. This diversity suggested a relatively complex microbial ecosystem rather than a single specialized species, unusual for such an isolated habitat, but not unprecedented in subglacial lakes. Kim proceeded to whole genome sequencing of several bacterial strains, obtaining complete genetic blueprints that could be compared against databases containing sequences from organisms worldwide. The comparison produced results that contradicted every expectation of isolated evolution. Approximately 30% of the genetic material showed close matches to bacteria found in hydrothermal vent systems along the East Pacific Rise, environments located more than 5,000 kilometers north of Antarctica in water depths exceeding 2,500 meters. The similarity extended beyond broad taxonomic classification to specific genes encoding metabolic pathways with sequence identity reaching 97% in some regions, levels indicating either very recent common ancestry or horizontal gene transfer between populations. Another 15% matched organisms from Antarctic coastal waters. Less surprising given geographic proximity, but still problematic, given the million-year isolation timeline. The remaining sequences showed varying degrees of similarity to organisms from diverse environments, creating a genetic mosaic that made no sense under standard models of evolution and biogeography. Kim expanded the analysis to include metabolic gene clusters, examining whether the Lake Mercer organisms possessed capabilities consistent with their isolated environment or whether their genetic repertoire suggested recent contact with other ecosystems. The bacteria carried genes for metabolizing compounds that should not exist in Lake Mercer's chemistry, including specific organic molecules typically produced by marine algae. They possess transporters for nutrients, abundant in ocean water, but scarce in subglacial environments. Their cold adaptation strategies match those of Southern Ocean psychrophiles, rather than showing unique mechanisms that might have evolved independently during million-year isolation. Contamination during sampling remained the most obvious explanation, though the protocols employed had been designed specifically to prevent it. Kim reviewed drilling records, sterilization procedures, and control samples taken from the drilling water before it entered the lake, finding no evidence of contamination. The control samples showed no bacterial presence, and the organisms recovered from Lake Mercer included species that had not been detected in any surface samples from the drilling site or support facilities. The genetic matches pointed to environments, deep-sea hydrothermal vents, and specific coastal regions, where the drilling team had never been, and from which samples could not have been inadvertently introduced. The alternative explanation required mechanisms for bacterial transport across impossible barriers. No geological evidence indicated recent connections between Lake Mercer and the Southern Ocean, the ice sheet having maintained continuous coverage for more than 1 million years according to multiple independent dating methods. Subglacial water flow could transport organisms between lakes, but Lake Mercer's hydraulic isolation had been confirmed through pressure measurements and dye tracing studies. Atmospheric transport could not deliver organisms through 1,000 meters of solid ice, and even if wind could carry bacteria to the ice surface, they would need to survive crushing pressure, extreme cold, and complete darkness during descent through the glacier. A smaller contingent of researchers suggested the genetic similarities might reflect horizontal gene transfer through viruses or other mobile genetic elements that could move between environments through pathways not yet identified. This mechanism could explain some of the observed patterns, but struggled to account for the wholesale similarity of metabolic gene clusters and the specific matches to geographically distant source populations. The Lake Mercer organisms carried not just isolated genes, but entire functional systems, apparently derived from environments they should never have contacted. The samples remain in frozen storage, their DNA sequences archived in databases where they continue to attract analysis from microbiologists attempting to reconcile the observations with known mechanisms of evolution, dispersal, and gene transfer. Each examination confirms the original findings while bringing no clarity to their interpretation. The organisms exist. Their genetic heritage links them to distant ecosystems, and the mechanism connecting Lake Mercer to those environments remains completely unknown, suggesting either that life finds pathways through barriers science considers absolute, or that assumptions about the lake's isolation require fundamental revision. Radio astronomer Dr. Thomas Reid isolated the frequencies from the aurora australis on August 9, 2014, filtering out natural electromagnetic noise, when his equipment revealed a repeating pattern in the very low frequency range, cycling every 11 minutes with mathematical precision for 36 hours before ceasing entirely. Reid operated a monitoring station at Mawson Station on the Antarctic coast, part of a network studying natural radio emissions produced by the Southern Lights. Auroras generated electromagnetic radiation across a broad spectrum when charged particles from the solar wind interacted with Earth's magnetic field and upper atmosphere, exciting atoms and molecules that released energy as both visible light and radio waves. The radio component typically appeared as broadband hiss, occasional bursts and whistler waves, emissions that varied chaotically with solar activity and magnetospheric conditions. The equipment at Mawson included antennas sensitive to frequencies between 1 Hz and 30 kHz, recording continuously and storing data for analysis. Reid routinely processed these recordings using software that separated different signal components, allowing him to distinguish between auroral emissions, lightning from distant storms, and human-generated interference from research station equipment. The August 9th recording showed all the expected signal types, but when he applied filters to remove known sources, a residual pattern emerged that should not have been present. The pattern centered at 18 Hz, with harmonic components at 36 and 54 Hz, frequencies low enough to propagate efficiently through the ionosphere and along Earth's surface. Each occurrence consisted of a brief tone lasting approximately 3 seconds, followed by silence of precisely 657 seconds before the next tone, a sequence that repeated with timing accuracy better than 1 second across 36 hours of observation. Reid initially suspected instrumental artifacts, perhaps interference from station power systems or electronic equipment cycling on regular intervals, but the frequency did not match any known source at Mawson, and the signal strength varied in correlation with auroral intensity rather than remaining constant as equipment interference should. Signal processing analysis revealed structure within the tones themselves. Each 3-second emission contained frequency modulation, subtle variations in pitch that followed patterns suggesting intentional encoding rather than the random fluctuations characteristic of natural radio sources. The modulation rate and depth changed between successive tones according to sequences that information theory analysis indicated carried entropy levels inconsistent with random noise. The signals resembled communication protocols in their temporal organization and frequency structure, yet they appeared only during active auroral displays and ceased when the aurora faded, linking them to natural magnetospheric processes despite their artificial characteristics. Comparison with artificial signals from radio transmitters showed similarities that troubled Reid. Human-generated communications used precise timing, frequency modulation, and structured repetition to convey information efficiently, characteristics the anomalous signals shared. Yet no transmitters operated at 18 Hz in Antarctica or anywhere else, the frequency too low for efficient antenna design and propagation conditions. The signals also lacked standard features of human communications, including error correction codes, synchronization markers, and the spectral signatures of amplitude or phase modulation schemes that telecommunications employed. They occupied a middle ground between natural emissions that should show no structure and artificial transmissions that should display different organizational principles. Reid documented 3 additional occurrences over the following 2 years, events on January 16, 2015, September 3, 2015, and March 27, 2016, each showing similar patterns but with different repetition intervals ranging from 8 to 14 minutes. The base frequency remained consistent at 18 Hz across all events, and the internal modulation patterns within each tone changed between occurrences, suggesting either natural variation in the generating mechanism or deliberate changes in transmitted information if the signals carried intentional content. The correlation with auroral activity held across all observations, the structured emissions appearing only when magnetospheric conditions produced visible aurora and ceasing when auroral activity declined below threshold levels. Attempts to locate the signal's origin through direction-finding techniques produced ambiguous results. The low frequency and the Earth ionosphere waveguide propagation mode meant signals could travel thousands of kilometers while maintaining strength, their apparent direction influenced by ionospheric conditions that caused reflections and scattering. Measurements suggested sources somewhere over the Southern Ocean or interior Antarctica, but triangulation from multiple receiving stations would be necessary to establish location precisely, and no other Antarctic facilities monitored frequencies below 1 kHz, with sufficient sensitivity to detect the weak signals. Magnetospheric physicists examining Reid's data acknowledged the pattern's unusual nature while struggling to identify generation mechanisms. Natural processes producing auroral radio emissions operated through plasma wave interactions and particle acceleration in complex turbulent environments where mathematical precision was foreign to the underlying physics. The 11-minute repetition suggested some kind of resonance or oscillation, but magnetospheric cavity modes and field line resonances occurred at different frequencies and showed different temporal characteristics. No known natural process combined the observed frequency, timing precision, and internal signal structure. The hypothesis that the patterns represented encoded information received serious consideration despite its extraordinary implications. If natural magnetospheric processes could generate structured signals indistinguishable from intentional transmissions, this suggested physical mechanisms capable of organizing electromagnetic emissions according to mathematical relationships without invoking intelligence. Alternatively, the signals might represent communication attempts from unknown sources using the aurora as transmission medium, an explanation that raised more questions than it answered regarding who might transmit and why such signals would appear only during specific auroral conditions. The monitoring continues at Mawson Station, Reid and subsequent researchers watching for pattern recurrence, while accumulating data that might reveal regularities pointing toward natural explanations. Each new detection confirms the phenomenon's reality while adding to the catalogue of characteristics that resist interpretation, leaving the structured signals suspended between natural and artificial classifications, their origin as invisible as the magnetospheric processes that produce the aurora itself. Cosmologist Dr. Angela Morales examined the South Pole Telescope's cosmic microwave background data on October 12, 2018, mapping the universe's earliest radiation, when she identified a cold spot 1.8 billion light-years. Across that, according to cosmological models, had a 1 in 1 million chance of existing. The South Pole Telescope, a 10-meter dish operating at the Amundsen-Scott Station, observed microwave radiation that had travelled through space for 13.8 billion years. Light released when the universe was only 380,000 years old and still cooling from the Big Bang's initial expansion. This cosmic microwave background provided the most detailed picture available of the early universe's structure, its tiny temperature variations reflecting density fluctuations that eventually collapsed under gravity to form galaxies and clusters. The standard cosmological model predicted that temperature variations in the cosmic microwave background should follow Gaussian statistics, their distribution determined by quantum fluctuations during cosmic inflation and the physics of matter and radiation interactions in the early universe. Observed variations typically measured a few parts per 100,000, regions slightly hotter or cooler than the mean temperature of 2.7 Kelvin above absolute zero. These variations showed characteristic patterns at different angular scales, their statistical properties providing tests of cosmological parameters, including the universe's geometry, composition, and expansion history. Deviations from predicted patterns indicated either measurement errors or physics beyond the standard model. The cold spot appeared in the southern galactic hemisphere as a region where temperatures measured approximately 70 microkelvins below the surrounding average, a difference small in absolute terms, but significant given the expected statistical distribution. Morales calculated the probability of such a large cold region appearing by chance through random quantum fluctuations, finding odds of roughly 1 in 1 million under standard inflation models. The spot's size amplified the improbability, spanning an angular extent of approximately 10 degrees across the sky, corresponding to a physical scale of 1.8 billion light-years in the current universe, after accounting for cosmic expansion since the radiation was emitted. Multiple independent observations confirmed the anomaly's presence. Data from NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, both space-based observatories that had mapped the entire cosmic microwave background at different resolutions and frequencies, showed the same cold region at the same location. The consistency across instruments with different systematic errors and observational approaches indicated that the cold spot represented real structure in the microwave background, rather than instrumental artifact or foreground contamination from galactic sources. Theoretical explanations divided into camps proposing either conventional physics, stretched to improbable extremes, or new physics beyond current cosmological understanding. The supervoid hypothesis suggested that the cold spot resulted from the integrated Sachs-Wolf effect, a phenomenon where cosmic microwave background photons lost energy traversing large underdense regions of space. A sufficiently large void containing far fewer galaxies than average could imprint a cold signature on the background radiation, though calculations indicated that even the largest known voids in the universe's structure would produce temperature decrements smaller than observed. The hypothesis required a void larger than any ever detected through galaxy surveys, a structure that would itself challenge understanding of how cosmic structure formation proceeded. Alternative explanations invoked more exotic physics. Some cosmologists proposed that the cold spot might represent a collision signature between our universe and a neighboring universe in a multiverse framework, the interaction leaving an imprint on the cosmic microwave background through mechanisms that remained poorly defined. This hypothesis attracted attention for its dramatic implications, but faced the problem that it made few testable predictions beyond the cold spot's existence and required acceptance of multiverse concepts that many physicists considered unfalsifiable speculation. Others suggested that the spot reflected topological defects in spacetime, cosmic strings or domain walls left over from phase transitions in the early universe, structures predicted by some extensions to standard particle physics, but never conclusively observed. Searches for corresponding structures in the distribution of galaxies at the cold spot's location yielded ambiguous results. Surveys found some evidence for an underdense region in the foreground, galaxies appearing less numerous than in surrounding areas, but the magnitude and extent of the underdensity remained controversial, with different studies reaching different conclusions. The difficulty stemmed from the challenge of measuring three-dimensional structure from two-dimensional sky positions, requiring accurate galaxy distance estimates that remained uncertain for faint objects at the relevant distances. The possibility of instrumental or analytical errors received thorough investigation despite confirmation from multiple observatories. Systematic effects from ground pickup, atmospheric emission, or inadequate modelling of galactic foregrounds could potentially mimic cosmic signals, and the South Pole's extreme environment might introduce unusual artifacts. Extensive tests found no credible systematic errors that could produce a spurious cold spot with the observed characteristics, leaving the anomaly in observational datasets without technical explanation for its dismissal. Implications for cosmology remained unsettled. If the cold spot represented a legitimate challenge to standard inflation models, it suggested that either those models required modification or that the universe's early conditions differed from theoretical expectations in ways that current physics had not incorporated. If alternative explanations involving new physics proved correct, the spot might offer the first observational window into processes or structures beyond the standard cosmological framework. The ambiguity reflected how single anomalies, however striking, rarely overthrew established theories without supporting evidence from independent observations and theoretical developments that could accommodate the discrepant data within a coherent framework. The cold spot remains embedded in the cosmic microwave background, its temperature deficit measurable with precision, while its origin continues to divide cosmological opinion between those who view it as a statistical fluke within acceptable probability bounds, those who see it as requiring conventional physics operating at improbable scales, and those who suggest it may indicate physics not yet understood, a frozen remnant from the universe's first moments that resists integration into humanity's current cosmological narrative. When geophysicist Dr. Lars Bergström reviewed the aeromagnetic survey data of the Dronning-Maud land interior on February 28, 2015, the magnetic signature showed a pattern of linear anomalies extending for 200 kilometers, their regularity and strength suggesting concentrated metallic deposits in patterns natural geology should not produce. Aeromagnetic surveys measured variations in Earth's magnetic field from aircraft flying systematic grids over the ice sheet, detecting buried geological features through their magnetic properties. Different rock types contained varying amounts of magnetic minerals, primarily magnetite and other iron oxides, creating local anomalies that revealed subsurface structure without requiring direct sampling or ground-based investigation. Bergström's survey covered a region of East Antarctica that had received limited previous exploration, a vast expanse of ice concealing bedrock whose composition and structure remained poorly documented. The aircraft flew at an altitude of 500 meters above the ice surface, maintaining precise navigation through GPS and recording magnetic field measurements at 1-second intervals, creating a detailed map of magnetic variations across the survey area. Most of the region showed the relatively uniform magnetic signature expected from ancient cratonic basement rock, small variations reflecting minor compositional differences in granite and metamorphic formations that constituted the continental crust. The anomalous zone appeared as a series of parallel linear features, each showing magnetic field intensity elevated by 1,500 to 2,200 nanoteslas above the regional background. The lines ran roughly north-south, spaced at intervals of approximately 12 kilometers, with individual anomalies measuring between 1 and 3 kilometers in width. 7 distinct lines appeared across the 200-kilometer survey extent, their orientations varying by less than 3 degrees from parallel, a consistency that geological processes rarely maintained across such distances. The magnetic field strength indicated substantial concentrations of ferromagnetic material, either near-surface deposits of magnetite-rich rock or deeper accumulations of exceptional size and purity. Geological context provided no obvious explanation for the pattern. The region lay within the stable East Antarctic craton, ancient crust that had not experienced significant tectonic activity for more than 500 million years. Linear magnetic anomalies typically formed along dike swarms, where magma intruded into fractures in the crust, solidifying into tabular bodies of iron-rich igneous rock that showed enhanced magnetic signatures. Such features appeared commonly in shield areas and rift zones, but they usually showed variations in orientation, thickness, and magnetic intensity, reflecting the irregular nature of crustal fracturing and magma emplacement. The Dronning-Maud land anomalies showed none of this expected variability. Depth calculations based on the magnetic field gradient indicated source bodies buried between 800 and 500 meters beneath the bedrock surface, placing them several kilometers below the ice sheet's base. At these depths, the magnetic sources resided within the crystalline basement, ruling out surface features or volcanic formations associated with more recent geological activity. The depth and magnetic intensity together suggested volumes of magnetized material measuring hundreds of cubic kilometers, scales that exceeded typical dike dimensions and approached those of layered intrusions or massive ore deposits. Comparisons with known geological features elsewhere revealed no close analogues. Layered mafic intrusions like the Bushveld complex in South Africa or the Stillwater complex in Montana showed strong magnetic signatures from their magnetite-rich layers, but these features formed in specific tectonic settings and displayed irregular geometries, reflecting their emplacement histories. Major iron ore deposits produced intense magnetic anomalies, but natural ore bodies formed through a variety of processes that rarely created linear patterns extending for hundreds of kilometers with such regular spacing. The Dronning-Maudland features seem to combine characteristics of multiple geological phenomena without matching any single formation type. Some geologists proposed that the anomalies represented ancient structures formed during Precambrian tectonic activity, perhaps remnants of a billion-year-old rift system or collision zone where iron-rich magmas intruded along parallel fractures. This hypothesis explained the linear nature and north-south orientation, but struggled with the pattern's regularity and the absence of other geological features typically associated with major tectonic events. Seismic surveys should reveal fault structures, basin geometries, or other evidence of past tectonic deformation, yet limited seismic data from the region showed relatively uniform crustal structure, without the complexity that major tectonic events usually imprinted. Others noted that the magnetic signature's intensity exceeded what normal igneous intrusions typically produced, unless the source bodies contained nearly pure magnetite, rather than the dispersed magnetic minerals found in most iron-rich rocks. Achieving such concentration required either exceptional primary magmatic processes or secondary enrichment through hydrothermal fluids that dissolved surrounding minerals while leaving magnetite behind. Both mechanisms operated in nature, but rarely produced linear features with the observed characteristics. The suggestion that the features might represent something other than natural geological formations attracted discussion despite limited supporting evidence. The geometric regularity, parallel alignment, and consistent spacing resembled artificial arrangement more than natural processes, though no mechanism existed for placing metallic structures at kilometer depths in ancient crystalline crust. The hypothesis required either ancient technology capable of deep excavation and construction, or natural processes that science had not adequately characterized, both explanations residing outside conventional geological frameworks. Drilling to sample the magnetic sources directly remains impractical, given their depth and the logistical challenges of Antarctic fieldwork. The features lie entombed beneath ice and rock, where only geophysical methods can detect them. Their composition and origin interpretable only through the magnetic fields they generate. Additional aeromagnetic surveys could refine understanding of their geometry and extent, but without direct sampling, the linear anomalies will continue to challenge geologists seeking to classify them within known formation types, or explain how nature created patterns suggesting organization across scales that random geological processes rarely achieve. Seismologist Dr. Patricia Wong monitored the seismic network around the Antarctic Peninsula when a swarm of small earthquakes began on May 4, 2020, at precisely 3:17 a.m., followed by identical swarms at exactly 24-hour intervals for 9 consecutive days, behavior that matched no known seismic process. The Antarctic Peninsula, extending northward from the main continent toward South America, experienced occasional seismic activity related to glacial processes, volcanic systems beneath the West Antarctic ice sheet, and residual tectonic stresses in the crust. These earthquakes typically occurred randomly in time and space, their distribution reflecting the chaotic nature of stress accumulation and release in rock under varying conditions of pressure, temperature, and fluid content. Wong's seismic network consisted of 15 stations installed across the peninsula and nearby islands, each recording ground motion, with sensors capable of detecting movements smaller than a micrometer. The network had operated continuously since 2015, documenting hundreds of small earthquakes and icequakes, while providing data for studies of crustal structure and glacial dynamics. Most detected events showed magnitudes below 2.5, too small to be felt by humans, but clearly visible in seismic records. The events clustered in certain regions where geological conditions favoured earthquake generation, and their timing followed no predictable pattern, appearing as random points scattered across days and weeks. The May 4th swarm began with 13 earthquakes occurring within a 15-minute window, all located beneath the peninsula's western coast at depths between 8 and 12 kilometres. The magnitudes ranged from 1.8 to 2.4, typical for the region's background seismicity. Wong noted the cluster in her daily review of seismic activity, but saw nothing unusual until May 5th, when another swarm began at 3:17 a.m., identical in timing precision to the previous day's onset. The second swarm contained 11 earthquakes within 14 minutes, their locations clustering within 5 kilometres of the previous day's epicenters, and their magnitudes showing similar distributions. By May 6th, the pattern's significance became undeniable. The third swarm commenced at 3:17 a.m., with temporal precision better than the network's timing accuracy could measure, suggesting synchronization to within 1 second across the 24-hour interval. Wong contacted colleagues at other Antarctic seismic networks, inquiring whether they had detected similar patterns, and received confirmation from stations on the South Shetland Islands that their instruments had also recorded the swarms. The geographic distribution of earthquakes remained consistent across events, each swarm activating the same crustal volume beneath the western Antarctic peninsula. Analysis of the earthquake source mechanisms revealed another consistency that natural seismicity rarely exhibited. The focal mechanisms, determined from the pattern of seismic wave arrivals at different stations, showed that all earthquakes involve similar fault orientations and slip directions. Normal faulting dominated, indicating extensional stress where blocks of crust pulled apart along fractures, but the precise repetition of both location and mechanism suggested that the same fault surfaces were being reactivated daily rather than stress distributing across a network of fractures, as typically occurred in earthquake sequences. The temporal precision posed the greatest challenge to explanation. Earthquake triggering mechanisms included tidal stress, changes in pore fluid pressure, and stress transfer from previous earthquakes. But none of these processes operated with 24-hour periodicity at precision measured in seconds. Tides affected solid Earth, with periods ranging from 12 to 24 hours depending on the tidal constituent, but the gravitational forcing varied continuously in amplitude and phase, sometimes enhancing earthquake probability and sometimes suppressing it. The observed swarms showed no sensitivity to tidal amplitude, variations that should modulate triggering if tides were responsible. Volcanic activity beneath the peninsula could produce earthquake swarms through magma movement or hydrothermal fluid circulation, but volcanic swarms typically showed either increasing or decreasing frequency over time as magmatic processes evolved, not perfectly repeating patterns. Monitoring of volcanic gases and ground deformation detected no changes, suggesting renewed volcanic unrest, and the earthquake depths placed them below the levels where magma chambers typically resided in the region's volcanic systems. Some seismologists proposed that the pattern resulted from periodic injection of fluids into the crust, perhaps through tidal pumping of groundwater or rhythmic discharge from subglacial reservoirs. Fluids could reduce friction on fault surfaces and trigger slip, and if the fluid source operated on a 24-hour cycle, it might produce the observed regularity. This hypothesis required identifying the fluid source and explaining why it would cycle with such precision, questions that remained unanswered. Ice sheet processes showed daily variations in meltwater production and basal water pressure, but these variations occurred primarily during summer when solar heating affected surface melting, not during May's Antarctic autumn. The swarms continued their daily recurrence through May 12th before ceasing abruptly, the final event occurring at the expected time with the same characteristics as previous swarms. Since then, seismicity in the region has returned to typical random patterns showing no temporal organization. Wong and her colleagues have published the observations, presenting the temporal precision as an unexplained feature that challenges current understanding of earthquake triggering mechanisms and seeking input from the broader seismological community regarding possible explanations. Monitoring continues across the Antarctic Peninsula, instruments recording each small earthquake, while operators watch for pattern recurrence. The 9-day sequence in May 2020 stands in seismic catalogues as an anomaly, its existence undeniable through multiple independent recordings, its cause uncertain despite extensive analysis of geological conditions, tidal forcing, and volcanic activity that might have imposed regularity on processes that typically operate without such precise temporal control. Shelf on November 7, 2021, analysing the sounds of ice movement, when signal processing software flagged patterns in the low-frequency emissions that matched the information complexity of structured communication rather than random natural noise. The Ronna ice shelf, one of Antarctica's largest floating ice masses, covering more than 400,000 square kilometres, generated continuous acoustic emissions as it flowed flexed with tides and adjusted to temperature variations and wind stress. These sounds range from low-frequency rumbles produced by ice grinding against bedrock at grounding lines to sharp cracks from fracture propagation, a constant symphony of mechanical noise that researchers use to monitor ice shelf stability and dynamics. Murphy's monitoring network consisted of 12 hydrophones and seismoacoustic sensors embedded at various depths within the ice shelf, installed through hot water drilling to positions ranging from 50 to 400 meters below the surface. The instruments recorded sound continuously, capturing frequencies from 1 Hz to 10 kHz, a range encompassing both the deep groans of large-scale ice deformation and the higher-pitched signals from small fractures and water movement in subglacial channels. Standard analysis focused on identifying event types, categorizing sounds by their frequency content, duration, and temporal patterns to understand the physical processes generating them. The anomalous patterns appeared in frequencies below 20 Hz at the low end of the detection range, where ice produced its most powerful acoustic emissions through slow deformation processes. Murphy's analysis software included algorithms designed to detect non-random patterns, tools borrowed from signal intelligence applications, where analysts searched for structured transmissions hidden in noise. The algorithms measured information entropy, Shannon complexity, and other metrics quantifying the degree of organization in time series data. Natural processes typically produced either completely random noise with maximum entropy or simple periodic patterns with minimal information content. The flagged signals showed intermediate characteristics, entropy levels suggesting neither random chaos nor simple repetition. Detailed examination revealed that the patterns consisted of sequences of acoustic pulses varying in amplitude and duration, the variations following distributions that information theory indicated could encode substantial data. The pulse trains lasted between 15 and 45 minutes, occurring irregularly, with intervals ranging from several hours to several days between episodes. During each episode, the sensors detected hundreds of individual pulses, their timing and amplitude relationships showing correlations across multiple timescales. Mathematical analysis found that knowing the amplitude and timing of previous pulses reduced uncertainty about subsequent pulses' characteristics, a property called mutual information that appeared in communication systems where signal elements carried interdependent meaning. The spatial distribution of the signals added to the mystery. All 12 sensors detected the patterns simultaneously, despite being separated by distances up to 80 kilometers, suggesting either a single powerful source affecting the entire ice shelf or multiple sources operating in coordination. Time of arrival analysis attempted to locate origins by comparing when signals reached different sensors, but the results proved inconsistent, the computed source positions shifting unrealistically between pulses within single episodes. The acoustic properties suggested sources distributed throughout the ice shelf's volume rather than concentrated at specific locations, as though the ice itself were generating the structured emissions rather than external processes imprinting patterns on propagating sound waves. Comparison with artificial signals revealed troubling similarities. Communication protocols used by submarines and other underwater systems employed low-frequency acoustic transmission because these frequencies propagated efficiently through water and ice. The patterns in Murphy's data showed temporal structure resembling phase shift keying and frequency modulation techniques that human communications used to encode information reliably despite noise and distortion. Yet no underwater vehicles operated near the Ron ice shelf, and even if such vehicles existed, their signals should show different spectral characteristics than the emissions embedded in ice-generated noise. Attempts to identify natural mechanisms producing information-dense acoustic patterns confronted the problem that ice physics operated through differential equations describing stress, strain, temperature, and fluid flow, processes that generated sound as byproducts of mechanical deformation or fracture. These processes produced acoustic emissions whose characteristics reflected the ice's material properties and loading conditions, but which should not contain the temporal correlations observed. Fracture sequences sometimes showed patterns related to stress redistribution, where one crack triggered others, but these patterns operated at much shorter timescales and showed different correlation structures than the recorded emissions. Some researchers proposed that the patterns resulted from complex interactions between tidal forcing, ice shelf flexure, and basal water movement, suggesting that non-linear dynamics in coupled systems might generate acoustic signatures with unexpected statistical properties. Computer models of ice shelf mechanics incorporating these processes produced sounds when translated to acoustic output, but the synthetic emissions lacked the information content measured in real data. The models generated either simple, periodic signals reflecting tidal cycles or irregular noise from turbulent processes, not the intermediate complexity that analysis algorithms flagged as potentially structured. The alternative interpretation, that the emissions represented intentional signals generated by unknown sources using the ice shelf as transmission medium, attracted consideration despite its extraordinary implications. This hypothesis required identifying what might transmit through Antarctic ice, for what purpose, and why signals would appear only intermittently rather than continuously if communication were their function. The questions multiplied faster than data could address them, leaving researchers with observations that defied classification within either natural or artificial categories. The acoustic monitoring continues, Murphy and colleagues analyzing each new emission episode while refining their signal processing techniques to extract more detailed information from the patterns. The data accumulates in archives where specialists in information theory, glaciology, and acoustic physics examine it from different perspectives, seeking commonalities that might reveal the mechanism generating structure in sounds that should be random. Whether the patterns reflect ice processes operating in ways current understanding has not characterized, or something residing in the ice that uses acoustic energy to maintain whatever functions it serves, the emissions persist, carrying information that instruments can measure, but that science cannot yet decode or explain. Paleoclimatologist Dr. Jennifer Cross examined the ice core samples from Dome C on March 19, 2023, using multiple dating methods to verify the timeline. When radiocarbon dating placed ice from 2,500 meters depth at 15,000 years old, while ice from 2,000 meters tested at 40,000 years old, an impossible reversal of the expected chronology. Ice cores extracted from the East Antarctic ice sheet provided the most detailed archive of Earth's climate history available. Their layered structure, preserving atmospheric composition, temperature proxies, and volcanic signatures from hundreds of thousands of years. The principle underlying ice core dating held that deeper ice was older, accumulation adding layers year by year at the surface, while burial and compression moved older ice progressively deeper into the sheet. Cross had participated in ice core analysis for 15 years, processing samples from multiple Antarctic drilling sites and developing expertise in the various dating techniques that established chronologies. The methods included visual layer counting, where seasonal variations in dust, chemistry, or bubble content created annual markers, radiometric dating using isotopes with known decay rates, and correlation with dated volcanic eruptions that deposited distinctive ash layers. These independent methods typically agreed within measurement uncertainties, their convergence providing confidence that assigned ages accurately reflected when the ice originally fell as snow. The Dome C core reached 3,270 meters depth, penetrating ice deposited over approximately 800,000 years, according to preliminary age models based on layer counting and ice flow calculations. Cross selected samples at regular depth intervals for radiocarbon dating, a technique measuring carbon-14 in trace organic material and dissolved carbon dioxide trapped in ice. The method worked reliably for ice younger than 50,000 years, beyond which radioactive decay reduced carbon-14 to levels approaching detection limits. She processed samples from 20 different depths, extracting carbon, measuring isotope ratios, and calculating ages using standard decay equations. The results from shallow depths matched expectations, ages increasing systematically, with depth in accordance with accumulation rates. Then at 2,000 meters, the age jumped unexpectedly to 40,000 years, far older than the ice immediately above and below. Deeper samples showed younger ages, the progression reversing in direct contradiction to stratigraphic principles. At 2,500 meters, ice tested at only 15,000 years, despite being 500 meters deeper than ice aged at 40,000 years. Cross rechecked her procedures, repeated the analyses with fresh samples, and sent duplicates to independent laboratories for verification. All measurements confirmed the inverted chronology. Visual inspection of the core showed continuous layering without evidence of folding, faulting, or other deformation that might have disrupted the stratigraphic sequence. The ice appeared as it should. Annual layers stacked in order, no discontinuities suggesting physical disturbance. Yet the dates indicated that time had somehow reversed, or that ice from different ages had been interlayered without leaving structural signatures of the process. Attempts to explain the anomaly through contamination failed when testing showed organic carbon sources consistent with atmospheric origin rather than introduced material. The inverted ages persist in core records, documented but unexplained, their existence challenging assumptions about how ice preserves climate history and whether chronologies constructed from Antarctic cores reliably reflect the passage of time. Whether the reversal indicates dating methodology, failures that similar anomalies at other sites have not yet revealed, or whether ice can somehow retain temporal characteristics that radiometric techniques measure, but that physical layering does not reflect, remains unresolved. The ice continues its slow descent through the sheet, carrying ages that defy the order in which they should appear, a frozen paradox that resists integration into frameworks assuming time flows in only one direction, and that the past, once preserved in ice, remains fixed in the sequence of its occurrence.